Yeah, they aren't as comfy as not shoes. Not shoes is so much more comfy. Yeah, I know, I don't love the focus, but...
Yep. Yeah, there's Basil and there's Amal. Amal is here. Amal, you're ready to... You want to come here so we can... talk? Yes, sir. Yeah, Basil was just finishing to eat real quick.
Okay.
But we're the full teams here.
Perfect.
We're good to go. We actually have a very nice ratio.
Yeah.
Because there's much less people today than yesterday. Perfect. All right. So.
Do you want to start, or do you want me to start? Like introduce them.
You can
All right,
start.
cool. All right, hi everybody. I'm Greg. Good morning. Thank you for all making it and drinking your coffees and being awake and excited to participate. Today we're going to be talking about machine learning, not using deep learning. This is more model-based approaches, using scikit-learn and nylearn. So we have the day kind of broken up into a few chunks. This is being run by Pierre, raise your hand. Elizabeth, raise your hand. Greg, I'll raise my hand. Jake will be here later. He will raise his hand then. And we have some TAs as well. We have Amal and Basil. Can you guys both raise your hands, please? And they're going to be helping as well. And basically what we're going to be doing is starting by showing you some basic principles of machine learning, with just kind of introduction to classification, regression, and measuring performance of these types of problems, or of your solutions to these problems. Pierre will then be going into unsupervised learning, parameter selection, and so on. And then we're going to have lunch, and then when we come back, Elizabeth and Jake are going to go into a specific neuroimaging example on this cool data set that you should have downloaded.
I wonder if people hear well.
Can you hear me at the back? Yes? Could you before I said that as well? Okay, perfect.
So it's my ears.
Yeah. Generally I'm loud, so I don't really worry about the microphone thing. But if anyone can't hear me, raise your hand and put a pink sticky note on your laptop. So some of you may have noticed that a few minutes ago I handed around sticky notes, and most of you should have one. If you don't, either figure out where they are in the crowd or get some from Elizabeth. You should have one blue and one pink. So what you should do is put them for now in a place where we can't see them. Now, if you have a problem, or you have a question, or you need support, or anything like that, what you should do is put the pink sticky note in a place where we can see it from the front of the room. And this can mean just like stuck to the edge of your laptop, so it's hanging off the side. And then one of our TAs will see it, come over and help you, and hopefully answer your questions. Now, if we're working on something and you're ready to move on to the next thing, if again we just have time where you're experimenting, what you can then do is put up the blue one, and we'll just know that it's okay to move on, because we're trying to make sure we are balancing. Some of you will come in maybe knowing a bit more than others, and we're just trying to, again, balance it to make sure we're not going too slow for everybody anyways. So does that make sense? Pink sticky if you need a hand, blue sticky if you want me to speed up. Cool. So the first thing we're going to do is just test our environments a little bit. So who here has Python on their machine? Show of hands. Awesome. That is, I think, every hand. Very close to it anyways. So that's great. So what we're going to do is, for starters, we're just going to download the code the code that we'll be using for the day. So what I'd like you guys to do is to head over to, this probably isn't visible, I'm going to get the sticky notes. Whoa, that's so close to the exact URL I need. Clearly this is the last time I used it. Let's see, so you want to go to github.com/brainhack101/introml. And once you're there, if you're familiar with Git, you can clone this repository. If you're not, then what I'd like you to do is just click this clone or download button and click download as zip. I'll put the URL back up. So everyone should do this. And what that'll do is it'll give you the actual essentially the code notebooks, the scripts that we're going to be running, and as well as the packages that you'll need to install locally so that you don't need to keep referring back to this website. So again, put up your blue stickies once you have this downloaded locally.
Can we adjust the focus a little bit?
Yeah, Pierre, do you know how to do that? It's quite blurry.
Oh, the quality of the projection, it's not good. We need to replace
The bulb? Okay.
not the bulb, the whole thing.
Cool.
We'll get done eventually, but not now.
Cool.
So
So I will just try to embiggen everything such that the blurry doesn't make it illegible.
Derek, do you think we could improve the sharpness? No, it's not. And maybe if you zoom a bit,
Yeah.
better. But,
I did that in the notebooks and I was asking earlier. Unfortunately, it's not going to be perfect, I guess. All the more reason, though, to download things locally so you can run them and just look at your screen rather than mine. Cool. So, show of hands, who has downloaded this repo, this bundle? Perfect. That's most of you. So, what I want you to do is, I'm just going to open a file explorer for the sake of it being consistent with what you guys are doing. So, I'll just download a zip. Go into, where's downloads? Unzip the zip file, go inside of it, and I see, you'll notice the same things that I see right here. Maybe they're sorted in a different order. Almost the reverse order, which is kind of funny. Cool. So now, the morning, we're going to be working on scikit-learn, so you can click on the scikit-learn folder, and you'll see there's a few things in there. So there's a few files that end in ipynb. Who does know what this extension means? .ipynb. Cool. So for those who don't, there's this technology we're going to be using today that I'll explain in a second called Jupyter. It essentially gives you these interactive notebooks. For those of you who were at the deep learning workshop yesterday, it's very similar to what you're working on in Google Collaboratory. And then the last file in this repository is something called requirements.txt. And what you'll notice is this is just a text file. It has a bunch of things that look like names of some kind, equals signs, and then numbers. So what this is it's a list of your, essentially your packages that we need installed for this to work, or at least the ones that I have installed for it to work, and the versions that we're using in particular. So what we're going to do is open up whatever shell you use to install packages. You guys can either create a virtual environment if you'd like. I'm going to also embiggen that to make it legible. And one more big. Cool. So that's better. So again, if you want to work in a virtual environment, what I'd recommend doing is something like virtualenv-p. I'm working with Python 3.6, so this is just specifying that. And then put your environment wherever you want. So I have a folder called env that I put my environment in. I'm not going to hit enter here because I already have my environment set up, but you could all do this, hit enter, and it would generate a blank environment for you. And then what you would do is you'd type source, env, I have an environment in there called scikit-learn, bin, activate, and voila. You saw my terminal change here. I got a red sklearn on the left. That means I'm now in my environment. Cool. So if I'm going too fast for anybody, again, please raise your pink stickies. So once we're in this environment, what we're going to do is just make sure we have the same versions of packages that I have. So we're going to do pip install -r requirements.txt. So essentially, pip install, pip, as again, any of you familiar with Python will probably know, is a package manager that allows you to download and install libraries. Install is the command that does this, or the subcommand that does this. -r specifies, instead of providing the names and versions of the packages you want to install in the command line, you can pass in what's this requirements file. And the requirements file can also be generated by pip, and I'll show you how to do that a little later. But essentially, we do -r, the path to our file, press enter, and it did a bunch of installing nonsense. For me, again, it said requirement already satisfied because I did this before because I didn't want internet problems to prevent me from teaching. Cool. So you should all now have an environment. So then the next thing we're going to do is one of the packages that was installed here is this thing called Jupyter that I mentioned. So what I want you all to do is to launch this Jupyter session using the command Jupyter-notebook. And again, I'll move this down so people can actually read it. Cool. So then notice that popped up a web browser, and it shows me now my notebooks. Cool. So we're in this environment, and I just as a quick sanity check to make sure everyone is on the same page, we are just going to open the intro notebook. And what I want you to do is just run through it. Again, I'll explain why all this stuff's happening in a second, but before we really even get into the meat of the workshop, it's just imperative you guys have working environments. So the way you run cells here is shift, then or you hold shift and press enter. This is equivalent to pressing the run button right here. So shift then enter, and then shift then enter, and then just keep pressing shift enter, and it'll march you down the page, and we have the first two figures generated. We can probably keep going. Just press shift enter a few times. Cool. So the notebook ran, and now once everyone can confirm that the notebook did in fact run, we will get started with the actual machine learning part of the workshop. And again, remember, if you're done and just waiting for me to move on, please show me your blue sticky note on your laptop. And of course, if you need a hand, show your pink sticky note and we'll come around and help. And if you don't have sticky notes, raise your hand and we'll give you sticky notes. Cool. Where are the sticky notes? Oh, there's some over here. Is there another stack somewhere?
Right here.
Perfect. Thank you. There's just you guys back there that need stickies. Anyone else? Show your hands. Cool. Bill hand them right there. Yeah. Cool. So I don't see a ton of blue stickies, but I also don't see very many pink ones. Yeah, perfect. So are you guys all on Macs or Linux? No, Windows. You have Python? Yes. Do you know how to install packages for your Python? Cool. How did you install Python?
No.
Yeah.
What's happening?
Okay, cool. You're the Windows expert?
No.
I can't do it by memory, but I can do it from seeing. Can you open an Anaconda shell instead of it? I think that sounds like a phrase I've heard before. Once you're inside there, if you can navigate to the folder with the requirements.txt in the notebooks, and then from that you can do everything else. Yep. So to go back to the installation instructions, so for those of you on a Mac, what you can do is, one sec, I'll just set up this terminal to be a little more readable. This one, cool. So for those of you on a Mac, you can open a terminal just by typing command space, open the spotlight thing, and type terminal. And then you'll get a terminal where you can interact with Python and run these commands. For those of you running on Linux, same thing. You should probably be familiar with your terminal. And for those of you running Windows, if you've installed through Anaconda, you will get an Anaconda shell, and you should open the Anaconda shell. Now, once you're in the shell, you want to go to the place where your projects are installed. So in my case, it happens to be in BrainHack 101 / intro ML. And then it actually happens to be in a subfolder called sklearn. Cool. So now I'm in this folder. I'm in this location where my where my files are. So what I'm going to do is I'm going to type virtualenv-p and Python 3.6. So the -p allows me to specify the version of Python I'm using. And in this case, I'm going to be teaching with 3.6. there's some differences between Python 2.7 or 2 point whatever and 3 point whatever. There's not very many significant differences within 3 or within 2. But for the sake of consistency and having nothing different for me, you should run 3.6 if possible. So then we're going to do this, and then I'm going to create an environment name, so like sklearn2, because I already have one called sklearn, as you may remember. So I do that, it'll create this virtual environment. Now it says done, perfect. So now I'm going to do source env sklearn2 bin activate. So what this essentially does is it makes all the libraries that are inside this virtual environment show up and be found when I'm trying to run my Python scripts. So I can do that. And what you may have noticed is that on your terminal, you should have seen something like, maybe yours might be in brackets. The name of your environment probably came up on the left of your prompt. So am I still with you guys over there in the front? No? So where are you guys right now? So I'm generally, if you're in the Conda shell, you don't necessarily need to create a virtual environment. So just as a quick clarification, I'm suggesting we use virtual environments mostly for the sake of keeping these executions and these libraries compartmentalized. So one thing that some of you may have experienced in the past is, you had some file or some code or whatever. It worked with one version of a piece of software, and then as soon as you opened it with another, everything broke. This could be true of, say, like Photoshop files or Adobe Illustrator files or Word documents or MATLAB scripts or whatever. So what virtual environments allow you to do is to have lots of different kind of compartmentalized sets of dependencies, so that if, for instance, you have one project that requires version X of some tool and another project that requires version Y, they won't interact with each other, and you can have both of those versions. So if you aren't comfortable with virtual environments, you can skip this virtual and source step. But regardless, once you're in a shell that has access to pip, you can do pip end in the location of your directory. You can do pip-r requirements.txt and press enter. Whoops, pip install of -r. And then notice again, it's doing a bunch of downloading and will install stuff for me. So if you're still having trouble with this, please, again, show your post-it notes and the TAs will come help, and then I'll move on to a bit more of the substance of the course. Cool. So where's the tutorial? Awesome. OK, so now to kind of start talking about actually machine learning now that we have computers that are all on the same page. So there are essentially two broad classifications of problems that we're going to be talking about in this workshop today. The first is classification. So show of hands, who here is familiar with classification? What that means? Cool. Can someone just yell and explain it for me? Amanda.
So you have labeled data and you're basically trying to predict the labels from
Right. That's exactly right. So again, just to say it again, in case you didn't hear, you have some labels assigned to your data, and you're trying to predict those labels from your data. So this could be, for instance, you have a disease classification. You have some patients and you have some control, and you're trying to predict based on some feature of these, whether it's a picture of their brain, whether it's, I don't know, their genome, whatever it happens to be, whether it's their blood type, whatever. You're trying to predict one class from another. So this can be really useful for a lot of reasons. I mean, this is the way medical diagnosis really works at its very root. So then the other type of problem is a regression task. So who here knows what regression is? Awesome. Can someone else blurt it out for me, please? I don't know anyone else's name, really, so I can't call on them as easily as I bullied Amanda. You, sir. Yes.
Well, it's when you try to find a linear equation that fits your data.
Right. So that's exactly right. So you were trying to fit an equation or model some relationship between a dependent and independent variable from your data. So linear regression is the most common, but there's also nonlinear regressions and things like that. Cool. So notice the first two plots we did in this intro notebook. So again, that we ran. They have a bunch of code that we won't look into right now, but we're going to learn what all these pieces mean over the course of the day. But what we ended up generating was here we have kind of two groups of points. So in a classification setting, what we're trying to do is figure out what the maybe cutoff is for these values such that, or the line that splits these populations, such that I can always say if you're above this line, you're class blue. If you're below this line, you're class orange or brown, whatever that color is. And then in the regression setting, what we're trying to do is essentially say, okay, I have a bunch of data. What is the relationship with this data? So that if I have another point that doesn't necessarily fall within my population, can I estimate y from x? So if I have a point that lands right here, can I predict what the y value would be? Okay. So essentially, the way we do this a lot of the time in a machine learning context is by working with this thing that we're going to be referring to as the data matrix. And it has an important organization. So the data matrix is essentially organized by, as a two-dimensional matrix where you have the number of samples as your rows and the number of features as your columns. So here, syntactically, we will have, again, the first thing in our index will be referring to rows, and again, the second will be referring to columns. So n samples. So this essentially means if I have 100 individuals that I'm studying, each one of them will represent a row. Now the features are essentially what properties of them we're looking at. So this can be, again, this can be age, this can be sex, this can be name, this can be whatever we want, some, again, clinical behavioral data. So in pretty much all of the settings we're going to be looking at today, this is how you want to make sure your data is organized. And it's really important to do this because if you don't, or if your data is even, say, the transpose of this, it can really make all of your findings meaningless and misleading because they won't necessarily be obviously meaningless. So it's really, I can't stress enough how important it is to really groom your data and make sure you're following this format before kind of proceeding to actually doing any learning. So one example data set that's used a lot in machine learning is this iris data set. So there's this picture essentially of these different types of irises. There's three types, Setosa, versicolor, and virginica. And they all have slightly different properties. So if we want to design a machine learning algorithm that can tell the difference between these types of irises, we have essentially a data set to try and do that. So remember that we need, again, a number of samples in rows by number of features array. So in this case, if we just look at these pictures, can someone just quick blurt out, what do you think the samples would be in this case? Someone said a word. Can someone just yell, what do you think the samples would be if we're trying to classify different types of irises? Yeah. Exactly, different flowers. Each sample is a flower. What about the features? So what are example features we could have from these images here? Could be color, yeah. Could be petal length, absolutely. Similarly, petal width. Right? So things like this. So properties of the flowers where we think they might actually be different from one another. Cool. So then what scikit-learn does as well is it actually comes packaged with a bunch of data sets, which is really nice. So what you guys should be able to see from this intro notebook, and again, from the most part, we're going to be typing things along. I'd rather you guys do that than just run the notebooks blindly. So I'm more just doing this one like this, so we all have, we made sure the packages were loading correctly. But so we can do, we can go from scikit-learn datasets to load iris, and we can first look at, okay, what is in this structure? So iris. If I just type iris, it'll dump it out. So we have these fields. We have data, which has a bunch of things in it, quite a lot. We have target, which has some stuff in it, target names, description. I'm pretty sure if I typed summary, it would give me, maybe it's print, just then it'll work that way. It should give me, well, it clearly didn't give me a very pretty version. But if I looked at, let's see, iris.keys, it'll tell me all the things that we have. Cool. So we have the data, we have the target, We have target names, we have description, feature names, and file name. Cool. So here's a bunch of things that come with this data set that they've given us. You can imagine that this is basically a CSV file, or a couple CSV files, because again we have the data matrix in one case. We have the target, so in other words, what label, which type of flower each of these observations is. We have the names of these targets. So again, if we did iris target names, we would see that we have these names here. Actually, I'll keep the other one above. If we did description, we would see a bunch of stuff that's not very prettily printed. Let's see if I can improve that. There we go. We have a bunch of information about this, so we can see that we have 150 flowers that we're looking at. There are 4 numeric attributes per flower. The attributes are sepal length in centimeters, sepal width in centimeters, petal length in centimeters, and petal width in centimeters. And then there's 3 classes: iris cytosa, versicolor, and virginica. Then they also have some summary statistics, so the minimum, maximum, mean, standard deviation, and class correlation with each of these features. And again, more description about these data sets, and you can look at other data sets as well that come in scikit-learn or nylearn, and they have similar descriptions where you can get a lot of information before really working on a data set to see if it's a good one for you to be practicing with before using or solving your real problem. So anyways, we have this data set that we just loaded. So again, we'll just confirm that it is indeed 150 by 4. So again, 150 is the number of flowers, 4 is the number of features per flower. So we'll just quickly look at that. Perfect. So now let's look at the first example. So remember the features that we had, we believe in order, were sepal length, sepal width, petal length, petal width. So if we look at these, just a quick sanity check. We have length is greater than width in all these cases, which makes some sense. We also have that that sepal is longer than the petal, which I forget which part of the flower the sepal is. So I'm just going to trust it, but that's a mistake, generally. So there we go. Cool. So anyways, what we want to do is now just look a little closer at this data. Again, make sure we understand it. So if we look at iris target, we'll see that the first 50 are class 0. So what class 0 here means is one of the types of flowers. And in that case, in particular, what we see is that it corresponds to cytosa. And then the next 50 are the second class, which is versicolor. The last 50 are the third class, virginica. Cool. So we're just going to quickly plot a scatter plot of this data, where we're just plotting 2 of these features, that is sepal width and sepal length. So just to make sure everyone's on the same page and can play with this data, what I'd like you to do is modify this plot by switching essentially these indices right here, the x-index and y-index, and see if you can come up with any pair of indices that are kind of more clearly splitting the data. So for instance, I just switched the x-index from 0 to 2, reran the plot, and then again we see maybe that this class over here, cytosa, is a little more different based on this feature. So if you guys can just play with this for a few minutes, see if you can come up with what you think is the best separation, and then once you think you have it, just show me your blue post-it, and we'll go on. And again, remember, pink post-its if you need a hand or have a question. That's a pretty good split. Okay, does anyone have any suggestions of what splits I should use, what axes I should use? What the values of x and y should be? Who thinks x, or what number do people have for x that gives you the most clear split of the data? Although I guess it doesn't matter. X and y is a better combination. Of course. Anybody want to speak up? 0 and 3? Cool. Let's see what 0 and 3 looks like. It's a great split. Cool. So we see that Setosa in this case is quite far off to the side, and there's very little overlap between these two. Awesome. Does anyone else have another one they like more? 2, 3? Yeah, I like 2, 3. It's a little more compressed. We still have that same overlap now. It's just on an angle. But again, we have a very clear separation away from Setosa.
You may just want to check who's behind, because I know that there are a few people who are really stuck at the very beginning.
Okay.
So
thank you.
let's avoid it.
Cool. So I agree. I think 2, 3 and 0, 3 are essentially equivalent, or they look very similar to me. There's almost exactly the same overlap, which is nice because we still have one class that's clearly separated. So before I move on, can I have a quick show of hands of who is not at this stage yet? Who is still struggling with the install or something like that? Show of hands if you're in that camp. Cool. So for those of you who are not, what I would like you to do is quickly open the Basic Principles notebook, click Source at the top, and that'll take you to a page that's kind of talking about this next lesson, and you guys can get a bit of a head start on the next lesson. So that you can, again, not feel like you're just sitting there waiting, or you can continue to play with this data and maybe investigate what other data sets come with scikit-learn. So what I'm going to do is just join the TAs, and we're just going to help. Again, I'll get you guys to raise your hands in a second, again, just to remind me who needs a hand, and then we're just going to make sure everyone's up on the same page. So again, can you just show me your hands if you need a hand getting up to where we are? Perfect. Show which so we know you're going to get the first feature was the density width, so if we change these numbers, then it'll change what's being plotted. Again, notice I don't know so all we were doing was switching this parameter right here, difference between 2 and 3. And then let's switch it. Does that make sense? Of course. Again, who else needs a hand? What it basically the reason why it's trying to is that the version of my requirements it wasn't the same material. So then what I'm saying is that upgrade it knows okay, I'm allowed to uninstall this because I'm just going to reinstall it now. See if that fits. Looks like it's
download. That's it. Yeah, and then you can upload. When you download it, then you can upload the notebooks on the web. Alright, so it's going to look like that. So you're going to go here, and you're going to go upload, and you go like, I don't know where you put it actually, just here,
Yeah, we're in
okay, so we know that that's some people on top of this. This is very useful feedback. I'm going to bring you Steve
and try running with this command again.
No, I see that you have your pink sticker out. Can you leave out
show of hands again, who needs a hand? Right there, and
It's so early for you.
so I could have my tutorial.
you got it?
So now I get speed reaction to this. But look, things are going well. I see a lot of stuff.
Yeah, that was set up for one part that you can do later.
If you get stuck on Slack,
so then what you could do is
to do is on the top right is upload.
again, I think that is
You can upload the notebook by here, and when there's you just need to install it. So, you know, then after you get that going, so like this you can follow the notebooks.
morning is and this is really only meant to we want everyone to see the box as much as possible. Because what we want is to make sure that we're still have a sorry about that. It looks like it. When did you install this? Go download this? Ah, that's fine. It's been we've updated it. That's a good idea. So if you just if you download a new one, it should all be there. So if you look at the new one, it should also be there. Start with that. All right, anyone else? Perfect, right. So what we want to do is I'll quickly just go through it. Cool. So you want to go to the website that's linked there. BrainHack 101. All right. Oh, sorry. I'm so sorry. You okay? Okay.
We're doing good.
Cool. So, thanks for bearing with us, everybody. It's always a little rough in the morning getting the environments configured. I'm going to move on to the second section. So, the next thing that we're going to be talking about before we get into, again, either solving classification or regression tasks, is just going through some basic principles of how sklearn works. So everything in sklearn that you'll be using to learn relationships on your data is wrapped in these estimator objects. So for instance, if we want to do linear regression, we would do from sklearn linear model, import linear regression. And this happens to be an estimator object. So we can create an instance of this using essentially by calling it. So we'll say it's a normalized linear regression, and then we can start to use this data or use this on data. So again, I'll just run through this notebook. So in general, it'd be good if we could go through these again by typing things, but since we're running a little behind, I'm just going to again sprint through a couple of them, and then when it comes to actually solving these problems on real examples, I'll try and slow it down. So again, we see that we have this model. So now, again, for any of you who are familiar with numerical processing in Python, you'll be familiar with NumPy, or NumPy, as you'll probably hear me refer to it as. So we're going to load this. What it essentially gives you, for those who aren't familiar, is the ability to create and work with matrices and arrays. So we're going to create two little arrays. We're going to have x, that is just 0, 1, 2, and y, that is 0, 1, 2. Perfect. So essentially, what we're going to do is stack these on, and what we end up with is this format right here. So now we can fit our model. Again, remember we set model before to be our linear regression. So we'll fit our linear regression. Notice that I got a warning. This is fixed in LAPACK. So this LAPACK is a numerical processing library that is used kind of at the core of NumPy. Depending on what system you're working on, whether you're working in Anaconda, whether you're working on Linux, you may or may not see this version. This just happens to be a warning I get because of the version I'm using and I have installed on my Mac. But anyways, so I fit my model, and now I can look at the coefficient, and we see that essentially our linear regression returned a coefficient of 1. Now, is this surprising to anybody, with our x variable being 0, 1, 2, and our y variable being 0, 1, 2? No, it's not surprising, because we made our data such that there's a perfect linear relationship with a scale of 1. So what we've essentially done, though, is learn the relationship between this data. So essentially going back one sec to the tutorial. Cool. So in supervised learning, which is again what I'll be talking about, we'll be going to unsupervised when Pierre takes over. We always have data sets that consist of data that has samples and features and corresponding labels. So we always have a patient that we know whether or not they have a certain diagnosis, or we have a flower where we know its classification. In unsupervised learning, which we'll talk about later, we don't necessarily have this training information. So in the case of classification, there are some, again, very simple techniques that we're going to go through to begin with. And what we're, again, trying to do is predict a specific label to which a sample belongs. So this means that we aren't necessarily trying to predict a relationship where if you have, let's say, I'm trying to think of the flowers example again. We aren't trying to necessarily say you are, if you have a sepal length of X, you are half Setosa and half Virginica, or something like that. We're trying to put specific, discrete classifications. So here we're going to load the k-nearest neighbors data classifier. This essentially says, from all of the data that I've trained on, who am I closest to? What is their label? That's mine too. That is what the k-nearest neighbor classifier is. And k essentially means how many neighbors are you comparing to. It's what we call what's the word for it? The regularizer, I believe. So essentially we're saying number of neighbors is 1. That means I'm only looking at my nearest neighbor. So we're going to load my data set. I'm going to fit my classifier where I'm only looking at my nearest neighbor. So again, this is simply saying that what type of a flower has these dimensions, where you put in any sample with these dimensions. So what's effectively happening here again is we've put in all our data, we've memorized it, and now given any new observation, what am I closest to? Let's say I'm that too. Does that make sense? Basically, of this massive field, who do I most look like? Let's pretend I'm the same label as them. So this is, again, like a very simple form of classifier. It's often a good place to start for lots of problems you're doing, because you always want to start simple and go more complicated rather than the other way around. So then let's plot, essentially, I'll explain what's happening in this cell in a second. So let's plot our data. So if we just use a k-nearest neighbor classifier, we're going to do 2 different ones this time. So first we're going to use a nearest neighbor of 1, and then we're going to also use a nearest neighbor of 3. So in the case of 3 nearest neighbors, what we're going to do is say, okay, who are the 3 closest people to me? What are their labels? I'm going to go with the most common one. Does that make sense? So in this case, you're not just looking at your closest partner. You're looking at, again, this group of other this group of close partners. So this is obviously going to be a little more stable because outliers will require more outliers to skew our results. So then we are just going to essentially say for each of these neighbors, we are going to create a nearest neighbor classifier using that number of neighbors. We're going to fit our model. We are going to, all of this is plotting code. And then this is also plotting code that just puts the labels on. This plots them. And so all the rest of this is plotting code. The only thing that's in our learning right here is this. Or well, I guess also the starting at iris. So again, if you understand this part that's highlighted, that's really the crucial part. So we load our data set, we get our, excuse me, we get our data. We then we get our class labels. We decide on what types of classifier we're going to use and the parameters of them. So again, k-nearest neighbor with neighbors 1 and 3. Then for each of these parameters, we instantiate our model or create our model and then fit it to our data. So then when we plot this, we end up with the following two plots. So first of all, which classifier do you guys think is better? Better object? Yeah.
None of them.
None of them. Well, first of all, yeah, that's a good point. It doesn't separate the data particularly well. That's a great point. Which one, though, if you had to pick one, would you say is better and why? The right one, the k equals 3, right? And why is that?
There's some blobs on the other side. So.
Right. So the important thing here is, remember this regularization parameter k, what it's saying is I'm going to assign labels based on the number of these that you're closest to. So in this case, if you are closest to the one thing that you're closest to, you get that label. So anything in this pocket happens to be closer to this outlier blue than to any of these greens or reds, where really they should probably be in the green or red category. Whereas k equals 3 is a little more stable. It might be less sensitive, but it's more stable in the sense that since there's only one outlier here, this will essentially be squashed by the rest of the model. Does that make sense to everybody? So this is an important, this kind of illustrates the importance of visualizing models, because depending on the properties of your data, you will almost always have outliers in one way or another, and it's pretty hard to kind of understand what's happening unless you're visualizing your data in weird cases like this. Cool. So does anyone have any questions about what we've just gone through there with kind of how estimators work and how we generally work with them in a classification context?
What's inside?
Pardon me?
What's inside?
What is inside of?
Inside of this function.
Inside of the function, right. So inside of this function is essentially the estimator. I mean, you can look at it. I can show you exactly what it is. But what it essentially is the model coded to whatever machine learning type of classifier or regressor it is, that is then being optimized over iterations. So there's a bunch of functions that exist for all these models, such as the fit thing, such as the coefficients parameter. So they're rich, full Python classes. But essentially, what it is doing that's different from any other classifier is it's just fitting the specific model that you want. So in this case, again, all the decision logic inside of this function is saying, who am I closest to, based on an average based over this many neighbors. So it's basically like a rank matrix. And again, you can look inside all these classifiers in terms of seeing their logic. The documentation is quite good, and also the code is open source. So in any case, what you can do actually is, here, I'll just quickly take this function, copy it. One nice thing about Jupyter is, well, there's two nice ways you can do this. If you open a bracket and you hold Shift and press Tab, what you'll get is a tooltip that pops up that shows you all the parameters that this model or function of any type really accepts. So in this case, we see that nearest neighbors is an option. It defaults to 5. There's a weights parameter, algorithm, leaf size. There's all these other parameters. And if we want to know more about this function, what we can actually do is at the start of the line put a question mark. Oh, and then again, run our cell. And what it'll do is it'll actually pop up a window on the bottom half here that shows more documentation about what the model's actually doing. So again, in this case, it's saying classifier implementing k-nearest neighbors vote. Read more in here, and again, all the parameters, what it returns, all the different features, how to use it, things like that. So that's a very useful syntax. Again, to get that little half window thing, you want to press, or you want to type question mark and then whatever your function happens to be. Of note, this will only work in Jupyter notebooks and IPython terminals. It won't work just in a normal Python shell or if you put it in any script. And then also, if you are in Jupyter notebooks and you want to do a more shorthand version, you can just do Shift Tab inside the brackets, and then you'll see what your parameters are there. Cool. All right, so let's see. All right, cool. So I just showed you guys an example of regularization in a classification setting. But this also applies to regression, of course. So imagine we have this this data. This happens to have been generated from an 8th order polynomial, I believe, and it looks like this. And say we want to learn the relationship between x and y on this data set. So there's a few ways we can do this. You know, we have a linear regression, and we can fit polynomials of different orders. So we can do a 4th order or a 9th order, or we'll plot the true distribution. And notice that the data in particular has been added noise, which again, in reality, all data will have some element of noise. So what we see here is, again, we've just created or fit a 4th order, 9th order, and green is the true line polynomial to this data. So obviously, green being the truth, which would you say is a better estimator, the 9th order or the 4th order? The 4th order. Even though the 9th order is, in terms of order of the function, actually closer to the true distribution. So this is an important point, though, is that generally what you want to do is prefer simple models over complex models, in part because they're easier to learn, and in part because they generally are more representative of contexts like this. So there's this whole, again, big area of literature that you should look into that's called regularization, and I'm just introducing it for the sake of something to be aware of.
And we're going to talk more about it
right
after the break.
Perfect. So yeah, after the break, we're going to be talking a lot about regularization as well. Cool. So now I'm just going to save that notebook. Great. So now we've gone through the basics. We've loaded some data. We've looked at the splits. We've done, we've mentioned regularization and the importance of it. And now we're going to go into a specific task that is a pretty common task you've probably seen if ever you've read a machine learning paper that's trying to do any type of image processing. You've probably seen something that does digit classification. So, there it is. So again, let's load one of the other scikit-learn data sets. It's called digits. So here, again, it's done the exact same way that we loaded the iris data set. So from sklearn.datasets, import load digits. Oh, and one line that I've completely ignored, not told you about, by the way, is this %matplotlib space notebook. This is what's called Jupyter Magic. What it basically does is makes it so the plots that you create are in your web page as opposed to pop out in a separate window. And it also makes them kind of interactive because they know that they're in a Jupyter notebook. In general, if you're writing a Python script, you wouldn't want to include this line. This is just for the sake of working solely in the Jupyter notebooks. Cool. So let's start by looking at our data. So again, we're loading this plotting library, pyplot, creating a figure. This is all plotting magic. And then in each location, essentially each of these little subplots, we are going to, excuse me, we are going to plot the image and annotate it with what number it's supposed to be. So again, here we do that. So notice some of these are pretty obvious, right? We have this 0 of handwritten digits, looks a lot like a 0. This 2 is kind of unclear, doesn't look super 2-ish. This 3, I think I understand. The 1s are pretty straightforward. This 2 looks a lot like a 1, and so on. And we can keep looking at these. Again, the 5 is actually pretty obvious. The 5s in general are pretty straightforward. Same with the 6. So let's say we want to develop a classifier that is predicting what number something is based on what we see. So we can start by looking at a couple dimensions of the data. So another technique that Pierre is going to be going into after the break is principal component analysis. It's a dimensionality reduction technique that essentially allows you to look at the portions of your data that are expressing essentially high variance, and you can look at more of these components to capture more of the variance, but in general the first component has the most variance of your data, the second most, and so on. So if, for instance, you have a very high dimensional data set like a picture of a brain, what you might want to do is some type of component analysis to reduce the dimensionality of that data, so you only have to look at, say, a few components rather than, say, like the million voxels in your brain. Again, Pierre will go into that in much more detail and explain it much better than I did, but it's just for the sake of what's happening here. Notice that this is just a low-dimensional representation of what's happening. So we see that our data is pretty clustered. all our images happen to look quite similar. There are some splits though, right? We notice that most of the colors internally are hanging out together. The reds are pretty much all on the right. The purples are kind of in the top corner here. We have the blues, the dark blues, the greens, like everything kind of, for the most part, has its own little cluster. The exceptions being the light orange that's floating through the middle and the yellow. And actually even the dark blue has some that goes up and kind of contaminates that space as well. So we're going to apply just a basic classification to try and see how well we can predict what number is being detected or identified based on the actual picture. So we're just going to start with naive Bayes classification, which is again a straightforward model where essentially you're fitting the probability of likelihood of membership in each class, and then picking essentially the class with the highest probability. So we are going to also do something called splitting, or data splitting, that we're going to talk about a little bit later. We're going to split our data set into a training set and a test set. The importance of splitting your data into a training test and test set, can anyone tell me why this is a thing we need to do? Sorry, can you say again?
Train our model and see if it's not overfit. We didn't overfit, so we have to.
Right, so this is incredibly important when you're trying to develop a classifier or a regressor. You don't want your model to overfit to your data. So for instance, say I train on all of my data, and then I test how well my model does on that same data. Well, in theory, I could have an exact perfect classification because all I did was memorize my samples. And what I'm saying is then, okay, I've remembered that this one, that this data point is in this class, so I assign that. And then it'll look like your classifier is terrific, when really it's just memorized your data. So that doesn't account for really any patterns that are underlying it. So what we really want to do is split your data into training sets and test sets. And again, there's lots of clever ways to do this, and to do this iteratively, and there's this technique called cross-validation that's in one of these notebooks a little later. But the point is we want to train on one part and test on another. So again, here we're having the naive Bayes classifier. We will fit it on our training data, and then we will predict outputs on our test data. Okay. So then we have now predicted, which is what we guess our test data is, and the expected is their actual true values. So now we're going to plot a value that shows essentially each of these digits, and it'll have a caption of whether or not, or essentially of the predicted number and whether or not that was right. So notice those in green, it's kind of hard to see. The green subscripts in each of these means correct classification. The red means it's incorrect. The number here is what it was guessed, and we can probably, for the most part, figure out what it was. So in this case, this 9 got read like an 8. This 5 was interpreted to be a 7. The zeros are pretty stable. This, I think it's a 3, got picked up as an 8. I think this is also a 3, got picked up as an 8. That was picked up as a 1, but I guess it's probably either a 4 or a 7, and so on. And we can kind of go through and understand where our classifier may be making mistakes. So let's just quickly try and evaluate what's actually happening here. How well did things go? So let's notice that, okay, matches. So we're just basically going to say which things did we correctly predict. So again, remember we set these two variables above. Predicted is what our model guessed in terms of what number we were looking at. Expected is the true values, and matches essentially is just the occurrence that pairwise each of these values is the same. So in other words, what portion of the time did we actually get it right? So the matches, we have, it'll be a 1 in those cases, 0 in all the others. So we had 375 matches out of 450 numbers. Okay, so that means that a performance of 83%. You know, not horrible. We could be doing a lot worse, but let's try and understand a little bit more about what's actually going on here. So we can import this other package from scikit-learn called metrics. So metrics, you get your classification report, and you can put in simply the label. So you don't need to actually feed in your classifier to this. You can just put in the expected values and the predicted values. So again, we'll plot this, and we will see these different scores. So we have precision, recall, and F1. So for those who are unfamiliar with these terms, precision is essentially the correct prediction of a true positive, or of the true value, recall is what portion of true values you correctly identify, and F1 score is essentially the area under this curve between these two. So these are very common metrics that are used that are used in machine learning. So here we have this broken down by class. So we can see, for instance, that we do very well with predicting zeros. We do okay with ones. We do very well with 4s and 5s and 6s. 6s are almost as good as zeros. We do worst on 8s. So again, we can look at this, what's called a confusion matrix, which shows us not only what, essentially how well we're doing on each number, but it shows us what our mistakes are being interpreted as. So for instance, the few times that we got, so the first row is, the first column is 0. The first time, so we got zeros right 52 of the 54 times. The times we didn't get it right, we interpreted as a 1, 2, 3, 4. We interpreted our 0 as a 4 a couple times. Let's see here. So now if we look at the number 2, we interpreted the 2 as, let's see, 3, 4, I guess that's 8. 8 a lot of the times. So again, by looking at this matrix, we can not only evaluate how our classifier is doing, but we can see what the problems are, and then we can maybe try and tweak our pre-processing of our data or the model such that it is more robust to these, again, particular errors we're noticing in our data set. So the diagonal is, so in this case, if any of you are familiar with like adjacency matrices, or this is the same thing, you have each row and each column are just a class. So we have the rows are 0 through 9, the columns are 0 through 9. At the intersection, we have 0, 0. That means that it is a 0 and it was predicted as estimated as a 0. If we at 0, if we are at 0, let's say again 4, yeah, 0, 4, that means it was written as a 0 and predicted as a 4.
But I have different numbers in there.
Yeah, so there's many reasons for that. One is that there's random seeds that need to be set in computers, and if I'm not sure if the script actually set one, but if it didn't, it's even possible that if I've run other cells before resetting the kernel, that things will be different. Is it in the same ballpark though, like in terms of performance?
Like I had 0 predict super accurate, and then it's 41%.
Okay.
But I didn't know it.
Yeah. So oftentimes when you do these like train test splits, it's doing random splits of your data, and if you want the most accurate results, that's actually a very good point, or the most consistent results is, did I import numpy here? Import numpy as np. You want to set something called the random seed. So np.random.seed, and then you'd pick a number. So that's usually the seed I use. And then what this will essentially do is set it so that every time you're doing anything that requires randomness, you'll be getting the same random numbers if you start from scratch each time. Or if you run things in the same order after you ran this random seed. So this is an important thing to do. An important thing to remember is that, again, if you want your results to be the stable across runs, set a random seed. However, what can be a bit of a trap that some people I've seen fall into is get results that they happen to get a good classification because their random seed, it was just lucky and they did that. So just fixing your random seed also isn't a solution to have like a highly performant classifier. It's just to make sure that you get the same thing from run to run. Cool. So does anyone have any other questions about digit classification? We're running a little low on time, unfortunately. It's 10:16. Yeah. And all these are online, so if I fail to cover everything, you guys should be able to find the resources. I think because Pierre's talking a lot about measuring performance and doing like parameter optimization, I'll skip this notebook and just go into regression. Yeah. Okay. Cool. So great. So any questions again on classification before we move on to regression? Cool. Awesome. So again, the source for this lecture is right there. Perfect. So now we're going to think of a regression problem. So again, here we don't necessarily have a class label. We don't have the same thing in terms of this should be a number 1 or this is a number 2 or number 3. Rather, what we have here is a bunch of features of housing data. So we have average number of rooms, the age of the house, the let's see, index of accessibility, radial to highways, tax value, all these sorts of features of Boston housing data. And what we're trying to do is understand what the relationship there is between these features. So it's not necessarily, we don't have these labels of like super big house, less super big house, more super, super, super big house. Like we don't have these concrete labels, we're just trying to understand a relationship in this data. So again, my notebook magic, load this data. And again, if ever you're trying to play around and don't want to use your real data that you're trying to use yet, you can look here and see what data sets scikit-learn comes with. There's a lot of them. So you can kind of mess around here. Again, the tutorials use most of them. So I think if you bounce around the site, you'll also find lots of good examples. Cool. So let's start by just plotting. Let's see, what are we going to look at? Look at the data. So this is just one visualization. What we have here, we have a histogram where we have price on the x-axis and simply the number of houses that fall in that category on the y. So, okay, this is interesting. We see pretty much almost, I'd say bimodal. We have this little tail that spikes up. We have more houses here and a bunch there. Now, what do you think could be some reason for why we have a bunch more houses here? Because that seems kind of strange. We'd expect there to be maybe a bunch in the middle and then it just to taper off.
Rich foreign buyers.
Rich foreign buyers? That's one option. I'm thinking of something a little simpler. Sorry? Did someone say something? Okay, so one thing is that notice how sharp the cutoff is here. Notice that we stopped at 50,000. I think that's the right unit. So notice we stopped, there's a hard cutoff there. So what likely happened is the way the data was collected, it was greater than or equal to this amount. So then what happened is everything that's in this category was squashed, or everything that continued to go up, and we have this long tail of expensive homes, was squashed down into this category. So it's an important thing to recognize about your data, and this is, again, a good reason why it's important to look at it, because if we're trying to fit a model to our data, what we don't want is the false impression that, oh, we have a boost of $50,000 homes. What we actually realistically probably have is something different from that, but this is an artifact of the way we've collected this data, and it's important to, again, consider that when we're making claims from it. Does that make sense? Okay. So again, let's look at just the data shape and what we have. So we have 506 homes, and we have 13 features per home. And again, just to confirm the targets, which is our labels or our prices, we have 506 as well, which matches, which is what we should have. So then we'll print data, our description. And again, we see that here are our different features. Again, crime rate, landing zone, all that stuff. So let's look at all these features. So this one takes a little while because it's big. Cool. So then we have, I need to just zoom out so people can actually see it. Excuse me. So in all these plots, we have price on our y-axis, and we have our index across our x. So let's see, what are some interesting properties we notice here? So I'll pick the easy one, and then you guys can jump in and point out some of the others. So obviously this CHAS feature is just a 0 or 1 labeling. It is either true or false. So we don't have anything in the middle, so it's important to know again that if we were doing or working on trying to use this to predict price, this wouldn't necessarily be a regression problem, this would be a classification problem. So what are some other interesting characteristics of our data? People can suggest them. RM, cool. What about that one? Seems like a good relationship. Is that what you mean, sir? Yeah, so there's a good relationship. And again, we have this funny thing where stuff flattens at our end, which is probably an artifact of kind of compressing our price range. Cool, what else? LSTAT. LSTAT's a cool one, yeah, that one's interesting. This one is, at first glance, almost appears to be the one with the fewest like outliers. of whatever shape we're perceiving, right? Because again, even in the RM, we had this weird spot up here, but here we have this nice kind of logarithmic curve. Cool. So if we look at this data, I'm going to embiggen again so we can actually read it. So now let's try and do just some simple linear regression on this data. So again, we're going to use our train test split to just split our data. I'm not sure if, I think Pierre will probably get into cross-validation a little bit. Okay, cool. So I won't worry about explaining that in the next few minutes. So again, we have our linear regression. We have our training set that we're going to train on. We're going to predict it. And again, use our classifier in our test set. We have our predicted values and our expected values. So notice this is exactly what we did before. So now we're going to plot our data. Again, where we have, where we're scattering our expected and our true. So we have on the x-axis our true price and our y-axis the predicted price. So the regression's okay. We, for the most part, get through the curve. Again, there's some weird outliers going here with our price here, where we're underestimating the value of these homes. Again, this could be due to our data compression. So again, okay, let's think, how can we do this a little better? So there's a slightly more complicated method of regression called gradient boosted regression, which essentially is a method by which you fit a linear regression. Then at the end you have a residual, so you have the distance from your data to that regression. So you fit a new regression on your residual, and you continue to do this until you get some performance or meet some number of iterations. So we do this and we get slightly better performance. Notice the curve looks a little tighter, and in general it seems to be doing a little better. So let's look at how well our model is doing, and we find that our root mean squared error is 2.67, which means that our root mean squared error is 2.67 excuse me, $1,000 away from what the true value of homes are from our predictor. So again, I realize I just sprinted through that, but the important point is that we have the way scikit-learn is structured and the way nylearn, which you'll learn this afternoon, is structured, is you have these well-packaged estimator objects that all have a very simple and consistent API. You can learn what they are by using, so you can learn what they are either by doing the question mark syntax I showed you before, or this tab complete syntax to learn what parameters they have. And then using them, you can fit, what you generally want to do is iterate through fitting the simplest possible model to your data, visualizing the results, trying to understand why it does or doesn't work, and then potentially moving to a slightly more complex model. But it's, again, the most important thing that I think is the takeaway from this is that you start simple and get more complicated. And you really need to look at your data to identify what type of problem it actually is. Again, I think we would automatically assume that we're trying to predict price from these features and assume that it's always a regression problem, where again, if we're looking at this feature, it's really more of a classification problem. And so looking at your data is the most important thing you can do with any type of learning. So with that, I believe my morning is done. We will have a brief break, and then Pierre will come in and teach you about unsupervised learning, measuring performance, doing cross-validation, and fitting parameters. Cool. Thanks.
We're going to take like a 15 minutes break.
Yeah, 15. Yeah.
Coffee outside. Please try to have the coffee outside if you can. We're not supposed to have food in there. And when there's food left, I get in trouble. And if you have issues with your local install, you may try to find one of us and try to solve them. Or otherwise, over lunch would be a good time. But I hope that in any case, through the binder link I've posted on Slack, everybody is able to follow tutorials. So we'll see you in 15 minutes.
Perfect. You can use your laptop.
Yep. a little announcement. Every week in Montreal, or almost every week, we had this thing called the Open Science Beer. So just a gathering of people interested in open science. It's called beer because we generally meet in bars, but you can drink, you know, orange juice, super juice, whatever suits you. It's really not like an alcohol-driven event. It's actually, you know, very well polished and very science-oriented. It happens to be today at the Mac Carroll pub. So that's that thing, Mac Carroll. It's an Irish pub. It's really a 5 minutes walk from here. It's going to be at 5:30. So it's kind of an ideal way of ending the day. If you want to stick around a little bit more, socialize, I think a lot of us are going to be there. So just Google it. You'll get a map. And I mean, it's big. You can host, I think, 200 people in there. So we won't overflow the open science beer. I mean, you're welcome every week. We've got a mailing list. I'll post it later. But you know, you can start by this week and see how it goes. All right. So we're going to start again. I guess it's about 10:45 right now. I can't read the time on my computer. It's half dead. But yeah, 10:45. Okay. So we are a bit later than we had originally envisioned. So I think we're going to really focus on two main tutorials. And if we have a bit of time, when we do at the end, we can go back to the smaller ones. But if we have to skip them, it's not a huge deal. I'd rather take my time on the important stuff. So before I really dive into the science, is everybody okay with their notebooks? Their Jupyter is spinning? I mean, I don't see a pink sticker, but I just raise your hand if you have trouble executing the notebook, so we make sure you can follow. All right. So as far as I know, you're all good. So I'm just going to close that down. So we're going to work on this example that's on the SciPy website. It's called the Eigenfaces example, chaining PCA and support vector machines. So you have the link for those lectures. That's the same thing that Greg was using. And also, just you get familiarized. Here I have my window, and up you've got a little zoom. So that's my attempt at making it more readable. Hopefully it works out. So it's a fairly sort of prototypical old school machine learning example. And what that means is that we're going to use support vector machine, which was all the rage in the 90s, but remain really in neuroimaging the top contender most of the time, because we have fairly small data sets. So in many current problems, deep learning really doesn't do much, and a linear SVM is about as good as it gets. Sorry about that, but that's just the case. And before we can run this algorithm, it can't really handle like huge data set, right? Like if you have thousands of features, the SVM may not like that too much. So what people typically do is that they do what's called a data dimension reduction. So they're going to sort of compress their data set into a space where there's less features. So those are the two key steps. So we're going to quickly look at the data, what it looks like, and then look at something called principal component analysis, which is the simplest way of reducing a data set. We're going to look at the support vector machine, and then we're going to look how to put them together with scikit-learn. And as you'll see, it's really just a couple lines of code. That's why scikit-learn is so popular, is that you can build fairly complex model and chain operations in only a few lines of clean code. All right. So without further ado, we are going to work on this notebook. It's on the repo where you had all the other ones, just not in the sklearn folder. It's just one step above. And this one is called Plot Eigenfaces. That notebook. So try to find that and open it. If you are on the cloud, you need to press upload and locally go grab the right notebook. Then it's going to be updated on the cloud. You just press on it to spin. Is anybody having trouble with that step?
Pierre, can you zoom in a little bit? It's a little hard to read or see what's on the bottom screen anyways.
So the bottom screen is really for me.
Okay.
What you need to look at, the top screen, it should be readable. All right? Okay. So the eigen faces problem. So really here what we've got is a bunch of faces, and we're going to be able to try to say who's who. Actually, in the neuroimaging literature, it's a pretty fashionable thing to do. It's called fingerprinting. So what you get is you have a bunch of data sets coming from different subjects, and each subject has, basically you want to know the identity of your subject by looking at the brain data. Here we're going to try to find the identity of our subject by looking at their face. So we're hoping this should be fairly straightforward, but actually it's a couple decades ago, that's really where the field was at. So what we're going to use is this data set called the Olivetti data set. So that's the first thing the notebook does. So you see we're importing from scikit-learn this data set library, the same one that you use with Greg. It gives you access to many existing open data sets with a very easy sort of interface to get them. And so this Olivetti data set, it was collected between 92 and 94. So it's an older benchmark. At the time it was gigantic because it was like tens of megabytes. And you got 40 subjects, and the 40 subjects have been pictured. The picture was taken 10 times. And generally, the background is always black, so it's pretty consistent where the face is on the image. But they're going to make funny faces, they're not going to look necessarily the same direction, the light may change. So it's still like it's a potentially challenging task, right? So when you execute that first cell, it should download for a little while, depending on the speed of your internet. If you find the internet very slow, by the way, we have 3 internet here. There's CREUGM, CREUGM2, and CREUGM3. So I would assume that most of you are on CREUGM, so if we switch, there's a good chance it's going to go faster. So the first thing we're going to do is just...
Unless you all switch.
Huh? Unless you all switch. So pick a number randomly in your head. Do division by 3 many times, see the remainder, and pick your Wi-Fi that way. And as an exercise, you can try to do that in Python. So we're just going to look at the shape. So the shape of that thing is 400, and that's kind of logical. We get 40 subjects, 10 images per subject, that's 400 examples, that's all good. Then the second shape is 4096, 4096. Do you know why?
Everything is concatenated?
Yeah, like the images, at least at this level of the structure, it's kind of a long vector. So 496 is something like 64 squared. So that would make sense. They're just little 64 by 64 images. Actually, fun fact, I've put you in that notebook the link to the original release. And actually, I like the website because it's kind of like going back in time a little bit. It's when I like really old school plain HTML page. And here it says that the data, they're like 100 pixels by, actually it's here. They're 92 pixels times 112 pixels. And that's a pain. So it's better to have it square and 64 by 64. So actually, if you were to work with that data set, probably that's the first thing you want to do. You want to actually get your data and make it nice. And actually, you'll find that when you do machine learning, a lot of your time is going to be spent making your data set nice. So joke goes that it's 80% of the work. I guess training the model is the other 80%. But you know, it can be very, very challenging. But in that case, it's all ready to go. It's the beauty of scikit-learn. We don't have anything to do. So I'm just going to go ahead, close that down, and go back to my notebook. All right. So let's just have a look really quick at what those images are like. So we're going to, first line here, we're importing something that's called PyPlot from Matplotlib, which lets you plot everything. If you're familiar with MATLAB, it's like getting all the plot functions from MATLAB in one neat package. And actually, that's something that Greg hasn't commented on, but for those people who are familiar with MATLAB, you generally don't import things. At the beginning, you set your environment, and all your libraries are set here. In Python, you can really be very granular, define what you want to use at any particular point in time, and oftentimes you're just going to import a function when you need it. So that's what's being done here. So the first line here really is saying, yeah, I want PyPlot. And actually something you can do in MATLAB, and which is awesome in Python, is that you can say, that particular library, I want to call it that way. So here we're calling PyPlot PLT to make our code nice and clean. But if I wanted to call it Toto or Tata, I could do it, and that's great. So here what I'm going to do is that I'm going to create a new figure with like subplots, grid of 8 times 6, and I'm going to do a little loop simply showing my images. And if I go in that data set, which I've called faces, now it's got this field or attribute that's called images. And in there, they are not vectorized. They're not going to be a long vector of 4,000 values. They're really a 64 by 64 nice little image. And then I can feed that in my plotting function. And what I get as an output is that. And you can try executing it locally. So basically, those 10 first pictures, I would assume are the same person. And then there's somebody else. I was able to tell despite the poor quality with the glasses. So just by looking at that, we can assume very likely we've got all our subjects stuck one after the other. So images 1 to 10 are going to be subject 1 or subject 0 because we're going to do 0 indexing somehow. Then the next image are subject 1, which is really subject 2 when you do mathematics correctly, and so on. So that here you have written what I was telling you, that those images usually would have to be processed and get nice, but here it's all done for you. So the first step when you do a classification is to define a training and a test set. All right? So, I mean, especially for those who were here yesterday for the deep learning workshop, that's something you must be very familiar with now, or at least the names. And the idea is that we really care about what's called error generalization. We don't really care whether we can fit a set of points with a model. And the reason why we don't care about it is that, like, unlike statistics, classical statistics, we use models that can fit anything. We're going to use polynomial of order 30 if we need to, or order 300 for that matter. So fitting things when you have that many degrees of freedom is really not hard. But you can fit points, but they will never generalize to new data that you haven't seen yet. So really our problem is to train a model, think about a regression line, that is going to be close to the point we haven't seen yet. All right. So to do that, if you would do it the old way, you would have this data set. It's got, like, you know, those 400 images. Each image has a given size, and you would, like, do a little couple of lines that would maybe, like, split those 400 images. You would say, keep 300 as your training set and 100 as your test set, and you would do that by, in MATLAB, indexing a matrix, an array, or something like that. Scikit-learn has a method for that. In general, there's a method for that. If you do machine learning and you're using scikit-learn, there's a method for that. That's what makes it nice. So we've got this method which is called train, test, split,
And the name is also pretty, you don't need a lot of documentation to understand what it does. It takes a data set, it splits it in train and test set. Yay for good naming practice. So what it outputs is you enter X and Y, which are the predictors, X, and the thing you want to predict, Y. So here faces has these two attributes. Faces.data is going to be the images, and faces.target, I haven't shown it to you, but it's just a long vectors with integers. So it has 10 zeros, and then 10 ones, and then 10 twos that encode just the identity of the subject. So you feed in X and Y, you feed in a random state, and Greg just told you why, so that if we reproduce that notebook, it's going to give us exactly the same results. But we could try to change the seed as well to see if it's changing our results a lot. And what it outputs is 4 things, 2X and 2Y. The X are the predictors, the Y's are the targets, and we've got a training X, a test X, a training Y, a test Y. Easy peasy. So if I do that and I look at the shape, well, my training X is 300 entries, and the second dimension, those are just images, so you have the 4096 pixels in there. And the test set is a 100 and 496. So it just so happened that by default, what scikit-learn tries to do is use 75% as your training set, 25% as your test set. It's not necessarily the greatest choice if you're doing neuroimaging and your sample size is 100, but we're still going to go ahead and keep the default for that example. Now, there's just there's a couple of details that goes into that, and if you want to actually look at the documentation of that function, what you're going to realize is that you can shuffle your data set when you do that split. Because if you don't shuffle it, essentially what you do is you keep the 300 first images at your training set and your 100 last images as your test set. But potentially what you want to do is sort of randomize things. So try to find 300 random images and as a training. It's actually the default. So here, if you were to have a look at the Y train, what you would see is that all the labels for the targets, they're kind of mixed up. You also have an option that you could make sure that you have the same proportion of subject 0, 1, 2, and so on in your training set and in your test set. That's called stratification. Imagine a situation where you want to predict old versus young. You want to have roughly, if your data set is half of young, half of old, you would want to have a training set that's 50-50 and a test set that's 50-50. So you want to stratify your training and test set. You don't want to go with random because you may end up with a training set that's just old and a test set that's mostly old and a test set that's mostly young. And then your model is going to suck just because you're training on data that doesn't make sense. Right? So stratification is another important aspect of splitting in test and train. But it's all like a few arguments you can add to that function. So it's fairly easy to implement. All right, so now we've done our split with one single call. We're going to go to our pre-processing. We're going to do the data dimension reduction. And here I'd like to know who has heard about PCA. All right, nearly everybody. Awesome. Who feels they understand well what PCA does? A substantially lower number of people. That also make a lot of sense. PCA is one of those things that's presented as something basic, but that's not. I think the general idea behind it is kind of easy to grasp. The actual implementation is really relying on beautiful old school math, which is eigenvalue decomposition. And, it's not extremely complicated, but it's not something that I can explain to you in the hour we have before lunch. So I'm going to stick with the high level, easy to understand explanation where you don't really understand what it does. Sorry about that. It's just not really the purpose. This morning we want to train a model. So what we're going to do is that we're going to go again in our scikit-learn, and we're going to import something that's called decomposition. And decomposition, that's a lot of method to decompose data. And actually, that's something you discussed a bit yesterday with Thomas, for those who were here yesterday. But essentially, all those decomposition methods, what they try to do is to take your data array, which is here, say, for your training set, you've got 300 example, and 4,000 features. And what you want to do is say, look, really, those 4,000 features, they're a mixture of a few sources. We may have like 10 factors that explain those variations. And if I mix them linearly, say, you know, I got age, I got size. If I do 0.5 times age plus 0.7 times size, that's going to give me feature 1, right? So the idea is that you have underlying factors, few of them, and that they're just mixing them, you can reconstruct your data set. You can imagine if the NSA was here and I put some microphone everywhere in the room, because they're very curious to hear what we have to say about this like machine learning stuff. You may have 1,000 microphones here because the NSA has a big budget. But really, at any given point in time, it's just me talking. It's boring, it's not very conversational. Hopefully you can interrupt me, don't be afraid. So then maybe there's 2 people talking, generally not at the same time. So you see what I mean, like there's a couple sources, a couple tape recording I could play and explain what's happening in those 1,000 microphones. Obviously, based on where the microphone is, they may not pick exactly the same sound. You know, maybe at the back they won't hear me as well as this guy. But essentially, those are just like amplitude adjustment on a few sources. And that's what a linear mixture is. You've got a couple sources, me talking, somebody else talking. You've got weights, whether the microphone is close or far, and you hear me well or not. And you just add them if they talk at the same time. And what you get is one of your features. And what PCA does is essentially tries to find the best sources to fit your data set. And it can do that for whatever number. So if you say, explain my data set with one source, it's going to take the average audio. You know, average everything that the microphone has picked up, so it's going to explain a lot of what you have in your data. If you ask for 2 sources, then it can do a little bit better. It can start like picking up maybe a few things from one of the speakers that spoke more, like me, and give him more weight in the second channel, and so on and so forth. So really, PCA is this iterative thing. It's trying to find the best source to explain what it can, and then it's going to regress that out from the data, and then work on the residuals and take it from there. So all your sources with the PCAs are going to be orthogonal, because they proceed with those like residual aspect every time. And you know, the more components you have, the better you can explain your data set. So now let's see it in action. That's the second line. Here I say I want to do a PCA and I want 150 components. It's already a pretty big reduction in dimensionality. Remember, we have 4,000 pixels in there. So we're going to try to explain all our 4,000 pixels with only 150 channels, sources. The other thing it does is, so that second parameter you see at the end, like the whitening, that means you're going to make sure that you're going to correct your data. So at the end of the day, your PCA decomposition, it has a 0 mean and unit variance. So when you look at the scores of the output of your PCA, you can sort of interpret them as these scores, you know, on a -3 to 3 scale, basically. So that's it. And then when you've created that model, then you can fit it to data. And as per usual in machine learning, when we fit, do we touch the test set? Do we fit on the test set? No. We don't want to mess with the test set. The test set is to test things. When we train, when we fit, we use a training set. All right. So here we fit on our training set, and that's about it. And actually, behind that, there's a lot of magic that has happened. There's a normalization that was done to our data, which is a good normalization. And then all the parameters of our PCA has been estimated and stored in that one structure. So we can carry it with us and then use it in the future to reduce the dimensionality of any data. What we have is really a generic new tool now to reduce images. Not just the images of the training test, any image that would be on the 64 by 64 grid. All right. So we can have a look actually at those PCA images. So one of the things it produces is a mean, because it does this standardization. So it subtracts the mean, so it keeps tracks of it. So we can look at it, and here you have a mean face. For those who knows the MNI template here? Okay, there's not that many images today. Interesting. I would have assumed like everybody. All right. So the MNI is a mean brain. We use a lot in neuroimaging. To compare different people, we typically like move individual brains so that they align with that like average brain. So that's the sort of like MNI template for faces. And just like the old style MNI template, you don't see a huge lot in there. You get the eyes, maybe the nose, you can guess, you know, outline of the face, no details. And I mean, you're probably doing already a pretty good job at fitting all your images. The mean probably explains like most of the variance in your data set. Because, you know, you get a black background, you get nose in the face. It's all you need to know, really, mostly. But then if you want to distinguish different people with just looking at the average, it's not going to be great. Essentially, what you're going to be capturing is the amount of intensity in your image, which, you know, doesn't tell you anything, really. So now let's look at the PCA component themselves. So we've got 150 of them, and each component is actually represented by an image. So why 150? Well, because we asked 150. And then each entry in that decomposition can be sucked off as an image, and we can actually look at it as an image. So here what we've got is that we reuse that PLT, the plotting function from Matplotlib. We do a little for loop, and we're going to look at our first images, and here they are in their glory. So here we have images with little lightning. Here we have images which have more light on one side than another. So it looks like the amount of lightning in the image is a huge source of variability in your data. And then when you start going down, well, you start seeing more interesting things. Let's say, I cannot really see from there really well, but I guess this guy's got glasses. This guy here probably has big lips, or at least very colorful lips. So, you know, we can make up stories about that, but PCA doesn't care about lips and glasses or anything. What he wants is explain variance in your data set. It just happens that, you know, some of the main sources of variance are also pretty easy to interpret for humans, like wearing glasses or not is going to change pretty dramatically the way your image looks like. But sometimes it can mix up a lot of things, and it's not necessarily easy to give a clear labels to those components. Sometimes it is, sometimes it's not. But fundamentally, you're doing just really a mathematical operation. All right. So now we are doing a couple of things. The PCA decomposition with fit, really what we have is those images that I shown up there. So they're like a basis function. Another way I find that is interesting to think about what PCA does is like Fourier transform. Have you heard about the Fourier transform? Yeah, huh? It's pretty standard thing. So essentially the idea is to represent a sound in a basis of sinusoids. And it has all kinds of funky properties that you can reconstruct your signal by just adding up sinusoid, and it's often actually a fairly efficient way of doing it. With just a few sinusoid, you can reconstruct sound, not too bad, kind of, especially when they're periodic. So what PCA are, it's your Fourier basis right there. Those are your sinusoid, but for images, and they've been built so that they can reconstruct those particular images really well. So they're like your own little Fourier basis for your data set that's really, really good at explaining your data set. Okay, so, but what we want really is to reduce our original data with that basis. And that, the PCA object, it doesn't have that. All he has is a basis, he has a Fourier sinusoid, but he doesn't have the Fourier coefficients yet. So what we want now is to find out the Fourier coefficients for our particular images we're interested in, and just keep that. So we're, in a way, what we're going to do is that we're going to move in Fourier space right now, and just look at the frequencies that are the most interesting for those particular sounds. If I was using this analogy. So what I do is that I use this PCA.transform method, and that takes a data set. Here I use my training data, and what it outputs is just the training data, but in the PCA space. So imagine that now I've got my Fourier coefficients to work with, and I just kept the low frequency because that's where it's at. So that would be it. I can do that for my test set as well. As I was telling you, the PCA object, it's found those basis functions. Now it can decompose any image. You could feed a lollipop or a flower in there and see what happens. It would probably not be great as a reconstruction because the basis has been trained to reconstruct faces and very particular type of faces. But you can feed any image that's 64 by 64 in that object. All right, so now if I look at the size of my training data in the PCA space, that is handily called X-train PCA, well, I still have my 300 images, but now instead of having 4,000 pixels, I got 150 coefficients, PCA coefficients. All right, so the test is kind of the same, except I have only 100 images, but it also has the 150 coefficients. And here what we've done really looks like nothing, but it's really powerful. When you do machine learning, if you remember, you don't want to touch the test set, you don't want to fit anything on the test set. And what we've done here is that we've learned an entire PCA decomposition, and we've used that decomposition to reconstruct or to compress our test set. But the decomposition was trained only with the training set. So there's really been no interaction. A common mistake of beginners would be to either PCA the test set itself, which then you don't use the same basis function and you're really messing it up, or not really compress their test set at all, in which case things would break anywhere because the test set wouldn't have the right size of your model. It would still have 4,000 pixels, or really we're going to train everything in dimension 150. But it's one of the key elements in machine learning. You want to try and normalize your test set the same way you've normalized your training set. Uko.
How much of a sin would be to do PCA in a full data set and then break it into test and training?
So the question is, how much of a sin is it to do the data dimension reduction, the full data, and then proceed as if we hadn't seen the test set? I would say small. The PCA doesn't know your labels. So it's not like you're going to bias your prediction because of that. To some degree. Maybe if your data set is very imbalanced, that could create problem, which you can handle with those kind of cross-validation approaches. You cannot handle when you work on the full data set. But I would say mostly it should be fine. But then it's like purists are going to give you slack for doing that. So it's really tempting, because the PCA can be, slow, and the data set is really big to load, so it's very tempting to reduce everything and take it from there. But if you want to do things rigorously, you really need to have your data dimension reduction part of your cross-validation. So use only the training set. So in short, I think in practice it doesn't matter a huge lot, but if you want to produce rigorous science, it's a big no-no. do not touch the data set. That's a rule.
Why is that?
Why is that? Because of the essence of what you're trying to estimate. You want to estimate how a model generalized to new data points. If that model has already seen those data points, then that's not what you're trying to estimate. I don't know what is it exactly you're estimating, but it's not it would be like a p-value where you would say, okay, I get a p-value of 10 minus 5, but really you've picked the smallest p-value in an entire image. I mean, who would do that? But that's this kind of analogy, right? You pick your model because you've already seen the data.
Yeah, but I mean, here are we in the making of, we are in the making of the model, but
yeah.
Basically we are data reducing here. So in the Fourier transform, would it matter if you choose your bandwidth of Fourier transform at the beginning, or choose it on part of your data?
Well, that's where the analogy with Fourier breaks, because the Fourier basis, we all know it. Here we're learning the basis. And really, I guess the analogy would be, you're developing a new biomarker to diagnose like multiple sclerosis. And what you want to know is how it's going to work when it's going to be deployed in another hospital. And maybe you could learn your normalization in that other hospital, but you don't know how much data you're going to have there. Maybe you have only like one data set. You can't like fit a PCA with one image, right? So really the question is, I got my training data here, I want to create my biomarker, and I want to know how it's going to work when I deploy it somewhere else, on data I've never seen. Now, you may find this is like too obnoxious and you don't want to do that, fine. In the truth, you may even be able to publish that, because the reviewers right now, they're not very well informed, and sometimes you see things come out in the literature that's not very rigorous. But I would say if you go with the traditional way, you don't touch the test set. Simple rule, right? Okay. So now we've got our data dimension reduction done. Awesome. It's time to learn something. So learn means the PCA, we haven't used the labels at all. That's why it's called unsupervised. We didn't know who was who in our pictures when we were doing the PCA. In other words, we haven't used Y. Every code line I've shown you has used X. But now we're going to use a Y. We're going to try to actually connect the X to the Y. Find a function so that ideally Y is f of X. All right? So we're going to look at a particular type of f that could map X to Y, and it's going to have parameters. We can call theta. Here they're like the weights, called the weights. And we're going to find the good parameters for our function so that it maps X to Y. So let's go ahead and do that. Once again, I mean, it's not super thrilling. You would hope that machine learning, being that like really badass thing, it would be lines and lines of complicated code, but absolutely not. What you do is import your SVM method. SVM stands for support vector machine. It's like a fairly standard model, as I said, quite robust. It says the two most popular right now seem to be random forest and SVM for smaller data set. Then here you initialize your model with the SVC class, because here we're trying to solve a classification problem, not a regression problem. Greg showed you 2 examples. So here it's more like we have 10 digits, except that instead of being 10 digits, 40 people. We've got some parameters. We're not going to discuss those, but those are called actually hyperparameters. They're not directly the weight. There are things that characterize the type of model you have. So it's the C and the gamma, and so we're going with those values because they work. And then what we're going to do is that we're going to fit our classifier, which we've called CLF. So it's got this little method called fit, and for that we're going to enter an X and a Y. And as an X, we're going to use our training X after PCA reduction, and as a Y, well, we're going to use our training Y. Because, you know, the training is just a set of labels. We don't need to reduce that. Yeah?
Sorry, one step back. How did we decide that 150 is a good number for...
So, you know, I feel I've wasted my youth answering that question. And I think in those cases, because 150 is a good number. is actually that response is much deeper than it looks. There is something you can do is how much variance you explain in your data set. Typically, people will keep 95% of the variance, kind of arbitrary, really. It's like, 5%, hello, Dr. Fisher once again, but, whatever. You can actually make that an hyperparameter. You can try multiple ones and find the one that works best. But, as a first go, if you really want to go like old school, PCN, 95% of the variance, good to go. You can actually pass that as a parameter to the PCA method. Here we fix the number of components, but if we had say 0.95, it would have computed that number for us to give us 95% of the variance in our data set. All right. So the third line, and the really like thrilling lines where all the action happen, here we found the F that goes from X to Y. It's not perfect, of course, but it tried to do as best it could with that little SVM model. It found the parameters for us, it estimated them, and now they're stored in our CLF structure. It lives in there. Just by calling the method, it's going to update the structure, and we can go and look at them if we want, but all the parameters of the model are not here. If you were on a regression line, seeing the beta coefficient, we said, I want a regression line. He said, OK. Then we said, fit y to x. He said, OK, here's your beta. It's 0.7. So that's what we just did out there. So now that we get our model, we can apply it to our test data and see the kind of label we predict. So we get a method for that. It's called predict. And what predict does, and I know that's something that confuses people a lot, because prediction usually it's like, you want to know what's in the future. Prediction when you read the astrology column with your morning coffee. Prediction in machine learning has nothing really to do with time, is when you try to predict y from x. So you find a function. It can be over time, but it can be just finding who's in the picture. So here it's that line here. We're predicting from a single image with our little model what would be the y, so what would be the index. And here the code is a bit more complicated, because what we do is show many examples in our test set, and above what you have is the number that was predicted. So for example, that second guy here has been predicted to be called 30. Yeah, people are called by numbers in that world. People are called 0 to 39 because we have 40 people. So here what we have is a picture of 30, or so thinks the model. And if the model is right, that number is black, and if the model is wrong, that number is red. And what you see that it's all black, because it all worked. Actually, on our first couple of images in our test set, there was no mistake made. So it was really able to, just by looking at the main variance in the data and looking at a very simple support vector machine, already associate the faces with one another, which actually is cool, because some of those people are doing funny faces. They're turning their head. It was not obvious at all that it would work that well, but it did. So good for us. We're going to make a tutorial with this. So exactly like Greg has shown you, we can now try to quantify a little bit more how good we are doing. And once again, scikit-learn has these very handy methods for us, which is called the classification report. So we are importing the metrics sublibrary of scikit-learn, and in metrics we have something that's called the classification report. And all we need to do is compute our prediction now for all our examples in one time. So that's a single line here. Predict for our x in the test in the PCA space. Once again, great naming convention. Doesn't really need comments up there. We get our y predicted, and that's what we feed in our summary, and then we make this nifty little table where for each subject ID from 0 to 39, it gives us a few metrics: the precision, the recall, and the F1, as well as the support So, I mean, Greg already told you about those metrics. Maybe who's comfortable with the precision metric? Okay, so actually maybe I need to talk again a little bit more. So let's say I get images and I have to predict who's in the image, and I predict it's Bob. Okay, so I'm interested now in the Bob prediction. The precision is simply the number of times I said, hey, it's Bob, and it was indeed Bob, divided by the number of times I said, hey, it's Bob. So we have a precision of 90%. So that means that 90% of the time I say, yeah, it's Bob, it was Bob. Okay. It's related to specificity, but it's not the same metric. The specificity would be really like how many times when I don't have Bob, I say it's Bob. And the specificity would be 1 minus the frequency of that. Here, the denominator is different. So it's very common in machine learning to use a precision as an outcome metric. And for people who are more from like classical statistics, they're more familiar with the specificity. The recall is sensitivity. And really, when you have precision and recall, you can deduce the specificity. So really, we're looking at kind of similar metrics. It's just that those folks like precision better. I like precision better as well, actually. I don't care so much about how many mistakes I make when there's not Bob, because, you know, it's going to depend a lot on how many times I have Bob in the data set. You know, if Bob is 99% of my data set, even if I make mistakes a lot, it doesn't matter because it's Bob. So if I say it's Bob all the time, I'm right almost all the time. And in medical imaging, that's a very common use case. If you look at autism, autism is 1% of the population. Being a control is like 99% of the population. So even if you have a specificity of 0.5%, it sucks, because you have 99% of people who are not autistic and you detect 5% of those. So even if you have 100% sensitivity and 5%, you know, false positive rate, you'll say people are autistic much more on control than on actual patients. So precision is a better metric in that case. What I want to know is that if I say the person has autism, what is the proportion of times that the person actually has autism? And specificity is a very bad indicator of that. You need to make math to understand what is really precision. So that's an aside. The F1 I'm not going to explain. And the support is very important. So here what I see is that in my test set, I have 6 images of subject 0. So subject 0 here is super important for me to know if I perform well or not. Well, subject 4, I have only 1 image. So really subject 0 for me matters 6 times as much as subject 4. Why? This is discrimination. We shouldn't accept that. We should fight that, and we should fight that through stratification. I mentioned stratification before. I could have made sure that in my test set, subject 4 is here as much as subject 0. And that would have been better. But here I didn't set that parameter, but when I look at my report table, I can figure out that, oh, I've messed that up. I really need to stratify this. Anyway, what we see is that we have perfect precision, and that the recall, the sensitivity is sometimes less than 1. I mean, there's every once in a while, like the odd little subject at only 50% precision, but if I aggregate over all of my subject, I have 93% precision and 93% sensitivity, which is strange, but sometimes math is strange. So that's it. The other thing you can look at is the confusion matrix. So right before our confusion matrix, each entry of the matrix was a digit. Here, each entry of the matrix is a subject. So the way I read that is that, say for subject, trust me, it's actually pretty complex to move that thing back. Like having those 2 split screens is a pain, but I'm getting there slowly. So if I'm looking at here, what I have is the number of times that subject 0 was called subject 1. Yeah. So in essence, what you can try to understand is like subjects that would be hard to distinguish. Yes?
When does F1 score matter?
So F1 is going to tell you if you get an imbalance between your specificity and your sensitivity. So it matters if you care about this imbalance. You know, at the end of the day, we could spend quite a while discussing about performance metrics, but it's just like, how tolerant are you to risk? Like, there's no good answer, and I feel like machine learners in the wild, they kind of like, they have their little fetish, a little bit like the 0.05 of Fisher. They like accuracy. But accuracy in many applications doesn't make a huge lot of sense. Of course, if you have an accuracy of 1, you know, everything's perfect, and then it's great. But in medical application, where we sometimes struggle with accuracy of 85, how good is 85 really? Do you have balanced class? Do you give the same contribution to control and patients? 85 in autism, if you don't adjust for the size of the classes, suck in ways that are not even funny. If you have actually a representative data set where autism is 1% of the population, if I set everybody as a control, I'm 99% accurate. Literally. That's the number. So you see, like, it's really important to know the size of your classes and to really understand if you care about specificity or sensitivity. And it boils down to your use case. You know, for Down syndrome, we've got tests that are very sensitive, we have tests that are very specific. Sometimes we do one after the other because there are potential risks to the tests that are very specific. So, you know, in the medical practice, that happens all the time. Like, people know that a particular test is either very sensitive or very specific and has very different use cases. So, you know, you can add as many metrics as you want, but at the end of the day, you're going to have to think about what's my problem and what do I really care about. If I run a clinical trial to try to fix beta amyloid in the brain, I want to have a test that's very specific to beta amyloid. Because if I start giving a drug to remove beta amyloid plaque to somebody who doesn't have beta amyloid plaque, I'm in big trouble. And fun fact, that's what the industry has done for a while, despite the availability of very specific tests, actually. But yeah, you need, there's no blanket answer, you know, what the right metric and when I should care about it. It really boils down to what's your use case, what problem are you trying to solve. If you can reach 100% accuracies, and that's great, you don't really need to worry about anything. But if you're in the real world and you haven't overfitted your model somehow, you're going to have to think about this. Okay. All right. So we get the confusion matrix. And just the last part of the tutorial is a fun little thing, because what it does is everything we just did, but in like 4 lines. So it's using that's called a pipeline, which again you're going to import from scikit-learn. It's got this like pipeline module, and pipeline module as pipeline function object. And then what you can do is to tell him, well, I'm going to have 2 steps. My first step is I do a PCA. My second step is I do an SVM. And then you plug the relevant methods from scikit-learn with the right parameters. And then that object can become like a mega method. You know, we created a PCA object, we fitted it, and then we applied it to make reduction. Then we created the SVM object, we fitted it, and then we applied it to make prediction. Here now we have this pipeline object, we can fill it, and we can use it to make prediction. And that's why like scikit-learn has this very clean, consistent API for tools, which makes them like pipelineable, which is very neat. So here we can fit our pipeline, and we can predict from our pipeline. And then we can also have a little confusion matrix from our whole pipeline. So basically, the only reason we did all those steps was more like to understand what we were doing. But if we want to create a model, we're in there. Also, here, it's not doing just a split training and test. It's going to do that a lot. And you can parameterize how many times it's going to try random split in training and test. That's called cross-validation. We're going to talk about that next. I think we have about 45 minutes left. What time is it?
It's 11:40, sir.
Yeah, 11:40. Great. Okay, so that exactly, we're right on time. so yeah, it does a full cross-validation for you and exposes it through parameters. So, I mean, the good old days, I mean, when I started doing a bit of machine learning, I would go on MATLAB, I would do my for loop, I would split my thing, I would, you know, you get the idea. My code would be 50 lines, not the end of the world, but there would likely be some bugs in there. And, you know, if it didn't, for other people who may be a bit less knowledgeable, for sure there would be, and probably I had bugs. So, you know, here having such compact model is great, and scikit-learn has about 1,000 contributors. I think about 100 which are very active. It's used, you know, throughout many large industries now. So, no, that code's good. So you can essentially, because it's so easy to review, it means that you have less chances of messing it up. And because the code behind is of high quality, there's a good chance you're doing meaningful science. So, you know, that would be definitely an incentive. It's easy to use and it's good. So I think like I'm starting to like sound like a bad advertisement. But I want to emphasize those things because I find for scientists it's something that's easy to overlook. As long as the code produces things that look right, we're going to assume and hope for the best. But the truth is that there's tremendous value working with tools that are actually well tested. So, you know, you get good results. And maybe we'll have less of those papers which claim for 100% accuracy predicting Alzheimer's 3 years before onset. Getting tired of those. All right. So, there's a note on facial recognition at the end. I haven't read it. You can read it if you want. But I want to just take that opportunity for like question. Because, yeah?
Really quick one. At the beginning you said that it's not very favorable to do 25%, 75%.
Yeah.
So
absolutely.
What would be more favorable?
So the question is, I mentioned that having a 75% training and 25% test may not be ideal. And really it's going to depend on two things. It's going to depend on the size of your data set, and it's going to depend on the complexity of your data set. Here we've got a relatively small data set, but it's also really simple. You know, you've got those like images, they're all in the same position, they're cut perfectly, they're fine. Just imagine 1 minute we won't go in the wild. We'd get just random picture for the internet which have a face. Now you're starting, you know, having tree, having shades, people can be in the top left, on the bottom right, it gets a mess. So, you know, it's really the balance of those two things that's going to determine, because you basically want your test set to be kind of representative of the world. So if you have those latent classes that, you know, you have 10,000 subclasses of like in the woods, in the city, with lots of light, with lots of shade, you want the test set to be big enough to have all of those, right? So I'm going to talk a little bit more about how like the different configuration and the kind of the pros and cons at a very high level. But I would say that kind of a consensus for data set in humans that are very complex and heterogeneous kind of by nature, and of moderate size, you know, we're talking 100 to maybe 1,000 would be actually sometimes even smaller than that. You would go with a 10% cross-validation scheme. And I'll touch briefly upon the rationale for doing that. Yeah.
Thanks a lot. So that was a very nice presentation of dimension reduction, and I wanted,
thank you, Christophe.
I wanted to compare with what we heard yesterday.
Yeah.
Because for deep learning, Andrew was keep saying that don't do anything on your data, use
yeah.
raw data as much. And what about dimension rate? Because in medical imaging we have high dimensionality and little data sets.
Yeah, so that's a great question. So 2 quick points. If you have neuroimaging data, register it. Don't ask your deep neural net to learn how to register data. That's stupid. It's a good thing. We know how to do it. We do it robustly. We have validated methods. Unless you're developing a deep learning net to register data, in which case, try. But if you want to classify autism, don't have your deep net register your data. So I disagree with Andrew that you throw away all preprocessing. I think there are some preprocessing which are good, and there's just no point reinventing the wheel. And I believe, some deep learning experts who's agreeing with me on that. So it's not as consensual as it may have sounded. But where Andrew is spot on is that what people would do in the past was like build features by hand. Maybe they're going to say, well, we're going to do a graph, we're going to have like 10% densities, and we're going to compute the efficiency of the network, which is just like a random mathematical operation on that binary matrix. But we're going to call it efficiency, so it sounds great. And now we're going to see if the efficiency of the network predicts Alzheimer's disease. And that sounds super exciting, that makes for a good title, but really, you came up with that metric. Why would it work? I have no idea why you think that works any better than any or random other operations you would do on a graph. So then I think it's great to have the deep learning figure it out for you, because it can try many, many different configurations, and you have a large data set, it can figure out what's the best one. So I think really what deep learning is trying to kill is feature engineering, not necessarily basic preprocessing. So that was part one of the answer. Part two is that there's a standard operation in deep learning which is called autoencoding, and that's exactly what a PCA is. You can think of PCA as a very simple linear autoencoder. You've got your data, and you get a linear mixture, and then you want to reconstruct your data, your loss function is squared, and then if you do that, you're going to learn in PCA. But you can throw in non-linearities, you can throw in a deep architecture, and now you can learn better autoencoding of your data. And maybe those are better representations really to do some prediction tasks. So there's this great paper came out of Benju's lab. It's called God.
It's called God?
Almost. It's always humility and simplicity from that lab. It could have been that, but but that's not it. It's not niche either. It's something like that. I'm going to try to find it again. But it's in genomics data. And what they do is that they essentially try to learn an autoencoder representation to maximize a simple sort of predictor problem. So they use the autoencoder latent variables, so the PCA coefficients, inside a fairly simple predictor, and they train both models together, and they found that even though it's genomics data, so they have lots of features and much smaller number of examples, they were able to solve meaningful tasks that were presented via NCF. And the name of the author escapes me, but she's at McGill. It's Prof at McGill, the main author, and the last author was Joshua. And I can try to find this reference for you. So anyway, even though in our situation we maybe not having like such large data set, you can still try to use the autoencoder that are non-linear, more powerful than PCA. And also you can do some kind of like a transfer learning. You can learn the autoencoding on a massive data set that may not have consistent labels, but then use those latent variables on a smaller data set to do some prediction. So I think there's lots of avenues right now that are not yet explored, actually, in fMRI at least, and that are kind of like a low-hanging fruit. Yeah.
You mentioned the word latent variable.
Yeah.
What does it mean in machine learning?
Latent variables, they're really the coefficients of your Fourier functions. So it's like an autoencoder does data dimension reduction, because if you don't, you can feed your input to your output and you're done. So, to train anything meaningful, you're going to need to reduce the dimensionality. And so you've got this middle layer, and those are the latent variables, and that's typically the representation you would use to then do some kind of like more supervised training. Now, sometimes they're called that way because you've got some additional constraints. Sometimes you're going to ask that your latent variables are distributed with a Gaussian distribution. So you force them to have a specific parametric distribution that can be useful, for example, to sort of like do interpolation between examples, like you've talked about GANs yesterday. So you're going to do those tricks, like you don't want to just reconstruct your data, you would reconstruct your data with Gaussian latent variables. So, typically when you use this vocabulary, you've got those additional sort of like assumptions that maybe you've trained them to have a specific distribution. Okay. All right. Yeah?
When you reduce the test set to
Yeah.
Did you use the same PCA class?
Yeah.
The same?
Yeah, absolutely. So that's a very important point. When we did it kind of step by step to break down what the pipeline does at the end, what we did is that here, here, we imported our PCA class, and then we initialize this parameter, and we fit it on the training set. And then that little PCA object we carried around. And when we reduce the test set, we reduce PCA, but there was no fit, there was just a transform operation. So I'm going to go and put that out for you. When we did the learning here, we trained on the training data, and when time came to do our prediction here, where X, so X test PCA, where is it generated? Here, see? We took PCA and we used the transform method, we applied it to our test set. All the parameters are inside the PCA object and they've been fitted on the training set. So that's what I was saying, even though it seems simple because the API is really beautiful, it's hiding a lot of complexity behind. And if you were to go like encode that line by line, you would need to do your training, carry your little matrices, make sure you redo the math to sort of do the projection from the PCA. So you would need also to do a little bit of linear algebra to make sure you apply the PCA to the test data from the beta that came from the training data. So you actually need to know what you're doing. So here, I mean, obviously you want to know what you're doing still, but it makes it harder to mess it up. All right. Other questions? Okay. So we're going to move on to the second half of the talk. So once again, it's really like all that you've seen is a copy paste from the SciPy lecture notes. So the part I want to discuss now is well, no, this one I don't think we'll have the time. It's important, but we need to pick up our battles. So it's the notion of like fitting the model and understanding when you've got a good model. And that's a question that came up yesterday during the workshop, and unfortunately I had the final exam of my class in the afternoon. I couldn't be there. But in the morning, I'm not sure that was made crystal clear. Like a few things were kind of assumed. So I'd like to go back and really discuss in detail what is our training error, what is our test error, how we expect them to behave, and when we think we've got a good model. What should our train error and test error look like that we say, now this is good, all right? And I'm going to start with this little schematic which you have discussed yesterday, which represent like 3 typical cases. Basically what you have is like a bad model, a good model, and a bad model. But the left model and the right model, even though both of them are bad, they are bad for very different reasons. So what we've got here is a quadratic function, really. So you can see the little points, they align almost perfectly with our little quadratic polynomial. So that's the truth. We've got a quadratic relationship here. So if we fit a quadratic function through those quadratic points, they fit really well with our data. It's a good model. We can see it. Now on the left, we've tried to fit a line through the same points. And that's not good. Because, I mean, with that few points, maybe it's actually good. We can't be really sure. But let's pretend for a minute really this is quadratic. On the left, the points tend to be far from the lines. And maybe if we had very few points, we could make sure to get the line really close to those very few points. But as soon as we're going to bring new points that we haven't seen before, for sure they're going to fall pretty far from our lines. So that model, the problem is that it's not flexible enough. So data has more complex relationship than the model is able to account for. So what we say here is that we've put a lot of bias. Bias? I don't know how to pronounce bias. We've put a lot of bias in our model. We're saying, we're neuroscientists, we know about the brain, so it's linear, that's going to be that. Too bad. It's not. So we've made too strong of an assumption in our model. Maybe we've picked the wrong regions of interest. That may happen. On the right, it's the opposite. It's like I'm Mr. Machine Learner. I'm going to do deep learning because like who does something else in 2018? So, let's go. And then you pass through every single point, which is great, I guess, except that the day you'll have new points you haven't seen before, you're going to be very far from your target. Because that thing is quadratic. It doesn't look at all like the blue curve here. Blue curves go crazy. So here, we don't have bias, but we have a lot of variance. The results of our model is going to vary a lot based on whatever data. Because essentially, we don't have enough data to really learn all the parameters of our model. So we can always try to learn it, but we don't have enough information, so we're going to do widely random guesses on those. So we're going to end up with something that on average would be the exact quadratic relationship, but we have crazy error bars. So a lot of bias, small error bars, but off target. Oh God. And on the right, you've got no bias, basically, but huge variance. So on average, you're on track, but your error bars are crazy big. And the situation in the middle is great because you've made the correct assumption, you tried to guess, and you guessed right. So you put bias towards the model, the right model, so you're going to have little variance and no bias, and that's really where you want to be. And now the question is, well, that was a nice story, but how can we make those kind of decisions in the real world? How can we quantify whether we're on the left, on the right, or in the middle? How do I decide my model is good model? And really the way we do that is through cross validation. So we're going to be fitting our model on a trained data set, X-train. We're going to then test our model on the test data set. We're going to make a prediction. So we're going to have Y test and Y pred, and we're going to compare the two. So by looking at those two numbers, the errors we do on our training set and the errors we do on our test set, we can pretty much distinguish between those three scenarios. And there's an additional degree of complexity, and I'd like to just at this stage build your intuition on it, is that really those decisions depend on how many points we have. If I have 5 points, there's no way in hell I decide if it's a quadratic function or cubic function or linear function. And in that case, probably I want to have linear. Actually, my friend Yomai, I find is hilarious because he does a lot of Bayesian modeling, and he has all those hypotheses of linearity. And generally, he tries to keep the data set small, because then the test of non-linearity, they're never significant. So then he starts validates his assumption, can go ahead. I'm not sure this is the wisest approach, but if you want to make sure that you have this very complex model, maybe this is the right model, but I will need tons of points to decide this is the right model. So doing model selection, deciding what the best model is, really intrinsically depends on how much data I have. If I want evidence for a very complex model, for sure I'm going to need lots of data to back that up. So those are really like the different ingredients we're going to try to explore together. So as per usual, there's a notebook for that with scikit-learn methods to do that inside. So that thing is called model validation, and it's up there. And I'm just going to check real quick that there's no other illustration from the SciPy notes which I need to go through with you before we go ahead. No, I'm good. So if you can just make sure to download, open model validation. who was familiar with that concept of like overfitting and like high bias, high variance? Yeah. Okay. So I mean, this is a sort of like a buzzword with machine learning. This notion of high variance, high bias. So we're going to try to unpack that on simulated data here. So what we get is we do this little function, and it's this sort of rational function with a random element in it. So it's going to give us a little parametric curve. It's not actually a polynomial. It's a division with polynomials, so that's called a rational function somehow. But we're going to try to fit polynomials to that thing, okay? And we're going to try to find a good model, a good polynomial to try to approximate this function here. So once again, we're going to try and control the seed and our mouse. And the seed is the easy part. And then we're going to generate random points x and apply our function y with a bit of noise. And we're good to go. We've got y equals f of x with a bit of randomness in it. So that's going to be our simulated data. So we're going to go ahead and just do what? Am I in the right notebook even? Yeah. Okay. I'm sorry. I forgot exactly the order of the notebook, but what I wanted to show you is here we're going to just look our data set. So we've got our x train, our y train, our x test, our y test. So we've done a split like we had done before. And we're just going to color them differently. So what you have is a bunch of points. The x are random. The y result for our little like parametric function we've created. And we've randomly splitted them, I would guess here 50-50. And we're going to go back and look exactly how we've split our test and our train. But in red you've got the train, and in blue you've got the test. So we're going to use the red points to choose our model, make our little line which is going to go through it. But then we'll be able to also estimate with a blue point if we are doing well or not with data that wasn't used by our model. All right. So, I mean, by now, after a day and a half, I'm hoping this is starting to sound awfully familiar. So I'm just real quick going back up. So here I've used my trusted method train test split to create those two subsets from the data simulated. And that's it. That's what I was doing before visualizing it. So now we are gonna just jump right in and make a pipeline. By now we know that we can combine operations. So we're gonna use actually a slightly different method, which is called make pipeline, and combine those two things, which is creating a polynomial model and then adjusting our polynomial model with a linear regression. Like I guess everybody's familiar with that concept. Like we've got a bunch of explanatory variables. One is an intercept, it's constant. One is linear. One is quadratic. One is cubic. If I have a model of order 3, and we're going to estimate 4 parameters: an amplitude for the intercept, an amplitude for the linear term, an amplitude for the quadratic term, and an amplitude for the cubic term. And that way I can fit a polynomial of order 3. So that's what I'm doing in that nifty little line here. Boom. I've imported those methods above. And then I'm going to try a bunch of different degrees for my polynomial. So that's stored in that degrees variable here. And I'm going to go essentially from degree 1 linear to degree 21. And I don't know the name for order 21 polynomials. I'm sure the mathematician found one out. They love that stuff, but I don't know. So after we made our pipeline, we can train our models, and something that's really cool is that there's this tool called validation curve, and then what it's going to do is that essentially it's going to try a range of parameters for our model. So we're going to reuse our training set again and again, and also look at our test set again and again to essentially try to figure out, which parameters works best. So what we do is that we call the order of our polynomial, the degree of our polynomial, hyperparameter. And here we're exploring the hyperparameter space to see which one is the best. And doing that typically is called model comparison. We're comparing different models with different hyperparameter set. So once again, scikit-learn, super clean syntax. We say we want to, our hyperparameter name is polynomial features underscore degrees. And that's because of this little method to build polynomials. That method has a parameter which is called like that, which fixes the degree. And in there, we can pass a vector with many different parameters we want to try. So this single line is going to let us try many different models. And when I do that, what I get is a validation score and a train score. So, here we don't talk about the test anymore, we talk about the validation. And the reason is that usually you test your model once at the end, but here we have many hyperparameters, and we're going to try many models on our test set. So now really we don't call it a test anymore, we call it a validation, because we're going to validate our best hyperparameter with the idea that when we have this best hyperparameter, we could try an independent test set later on this one model that works best. And here it is, it's beautiful. So what you have on the x-axis is the x-axis. I feel this whole morning is a long Dr. Seuss experiment for me, it's terrible. On the x-axis you have the order of the polynomial, and on the y-axis you have your accuracy. And what you can see is that for very low order polynomial it's bad, which we would expect. A line doesn't really go well in that nonlinear function, and then it sorts of plateau. But there is a very interesting phenomenon that happens. That at the beginning, the training error and the validation error, they follow each other very closely. So in a sense, by making my model more complicated, I'm able to better fit my data points, and that generalizes very well to points I haven't seen. Actually, just as well. And right there, about order 4, it starts to diverge. I can still fit better and better my points, so the orange line keeps going up, but it doesn't regeneralize anymore to the new points. I keep getting small improvements in terms of the generalizability, but it sort of plateau. And then actually it starts being worse. So when I start getting very complex polynomial, actually I don't generalize as well to new points. So there's basically 3 regimes here. On the left, clearly I'm having too much bias. By having models that's more complex, I can fit better my data points, and that generalizes well. So on the left of the graph, I have a bad model, just like the model that was on the left in the little picture. On the right, I get great fit with my data points, but it doesn't generalize. So I have a bad model, the model that was on the right at the very beginning. And in the middle, I have good models. Now, what is the best model? I don't know. They're probably all interchangeable here. But I would say that as soon as it plateaus like that, it means you're starting to overfit. Like if you fit more your data points, but you don't get substantial gain in your generalization, that means you're starting to waste your degrees of freedom. You're fitting a model more complex, and that doesn't really work better. So it's the, I guess, the Occam razor principle, like keep it simple. If it doesn't help and it's more complex, don't use it. So really the sort of like rule of thumb would be to probably stop your model right here. Or right when it diverges. And you could go for really the maximum of the validation error, or you could just start stopping right when it diverges. Yeah.
Because ideally you would have a further like testing set.
Yeah.
Test where this point lands in an untouched data set.
Yeah, well, when you decide for your hyperparameters, I mean, this is a real life kind of thing. You've got your degrees, you don't know it, and maybe you've got the CN gamma parameter for your SVM to choose, and you're going to try a bunch of them, and at the end of the day, you're going to want to sort of find the model that works. But definitely, now you've tried so many models, you have a p-hacking problem. You have a multiple comparison problem. If you want to make sure that that model actually generalizes well, you know, if you tested 500 models which actually all perform the same, for your particular data sample, one will be performing best. And so then that metric of performance is biased. You cannot trust it. If you really want to know how good it is, you need a separate test set, yes.
Could you explain why there's like a bump when we go really, really high after certain, when it gets really, really complicated, there's a bump?
All right.
It looks like it's getting better.
There may be some profound reason for it which I ignore. But you need to realize that those accuracy scores, they're a bit like permutation p-values. Like, who here does permutation testing? I've already done permutation testing, only a small fraction. All right. So what you have is your accuracy score is really an average of zeros and ones. Zeros when you were wrong, ones when you were right. If you have 100 test example, you have an average of 100 zeros and ones. That's an average of Bernoulli variables. Like the statistic of that is very well understood. And when you have only like 100 example, actually the variance of those numbers is pretty high. So you can't, you know, if you improve of 1% accuracy, probably it's meaningless. I mean, unless you have a data set with 1 million examples in which any change is significant, you really need to make stats. So in traditional machine learning, especially deep learning, they've got those massive data sets. So they don't even bother doing statistics because, you know, any tiny change is significant. But for us medical majors, it's not the case. So, you know, I would say this is a random bump. Long-winded answer. All right. So I would say that graph pretty much tells you, you know, what's a bad model, what's a good model, and there's two ways of being a bad model. It's like, you know, underfitting on the left, overfitting is on the right. Anything in the middle is kind of okay. Keep it simple. As soon as you reach that plateau, you can stop training. And yeah. So, but here we've tried with a given number of examples. And as I said a bit earlier, maybe that model selection is going to change if we have more data points. So that's another experiment we could try and do, because we actually have control about the number of data points our model does. This is because we do cross-validation. So we could try to actually start with very small training set, then a bit bigger training set, and a bit bigger training set, and see how that impacts those curves. So what we're going to do is that we're going to work at, for 1 degree of polynomial, so we're going to look at degree 1, just a linear relationship, and we're going to try to fit the model with increasingly larger training sets and see how that impacts our training error and our validation error. So that's what comes next. That's a long text that explains just what I said. So those objects are called learning curves, and really they try to explore the relationship between validation and training errors versus the amount of data you have. And once again, I mean, it's almost frustrating at this stage, like it's like all those one-liners. So we've got this tool that's called learning curves, and we're gonna simply call learning curves with our model and our data. And yeah, all right, sorry, I had a hard time seeing. So here we're gonna say we're gonna try different sizes for our training set. We're gonna go with a logarithmic scale and test different sizes. And then we call the method, it does a curve for us, and then all we have to do is to plot the validation score and the training score as a function of our training sizes. And here, somewhere in there, I've set the degree to 1. Yeah, the second line up there actually says, work with a degree for your polynomial of exactly 1. And here's what it's going to look like. So if you have barely no data, it does poorly, okay. But as soon as you have data, it converges. The training set equals your test, your training accuracy is the same as your validation accuracy, and they suck. So that's a bad model, consistently a bad model. It's not really an artifact of how much data I have. Whatever the amount of data I try, it's basically fitting right, but it's under-fitting. I know I can go much higher than this. So that kind of confines what our intuition was, that in that regime, for those type of polynomial, we're really under-fitting, and this is not an artifact of the quantity of data we have. Okay, so you almost asked a question, and I'm almost ready to answer.
Digesting.
Okay, take your time, it's fine. Anytime if you're ready.
What are the x and y axis here?
So x, that's a very good question when you present a graph. So the x is training size, or how much examples you had in your training set, and the y is your performance. So validation score and test score, and yeah, there should be a legend here. I may have omitted to replicate the legend. Sorry about that. The legends are in the SciPy lecture notes. So. All right. So that's an under-fitting learning curve. Yes?
What's that warning about?
Oh, the warnings, they're everywhere. It's a real, I love Python for many aspects. The warnings have to go at some point. So I believe that Jake starts his notebook by saying, I don't want to hear about your warnings, because they're warning me all the time. And that in Python 3. In Python 2, you're going to be submerged by oceans of warnings. With, if you like to read warnings, but...
that's a meaningful warning.
Oh, that's a meaningful warning, my God.
Not a parameter.
Oh, God. So I'm so used to ignore them that you see, it's a very... all right, so... Oh, yeah. So no, that's actually a great point. Here I've used a default for my cross-validation scheme, and it's telling me, don't do that. Think about how you cross-validate. It's very important. What time is it, Elizabeth?
It is 12:20.
All right, that's perfect. We have 5 minutes for a quick discussion about how you cross-validate things. So the warning is that you shouldn't be using a default for this.
How many partitions?
It's a default. I don't. It's 3.
I think it's 3 is the default.
Elizabeth thinks it's 3. That's the default. And we can investigate. Actually, you can investigate. Create a new cell, pop the documentation. I mean, all this is executable. You can try things. Actually, you should probably try degree 4 to confirm it's a good model. But in the meantime, I'm going to go and try degree 15, which is a bad model. So it's same code, except I've changed the 1 by 15 on the first line. And here it is, and that is a terrible model. So what we see is that in orange we got the training error. So it's the performance of the training data is excellent. I'm fitting all my points, but my test is really struggling, and it's really at the beginning horrendous because I don't have enough data points to fit my polynomial. So the polynomial goes crazy. It gets those like gigantic test errors. At some point, it finally starts to behave like I have enough data point to fit 15 parameters in that polynomial, finally. But still, it never quite catches up with the test set. Now, I've got a cap on this experiment, right? I have only so many examples to try. So maybe if I actually generated thousands of examples, the blue curve would slowly catch up with the orange curve, and I would find a point where really I could fit a nice 15-order polynomial on this. But at least based on the quantity of data we have, this is clearly overfitting. In that regime, in that data set size, a order 15 polynomial is overfitting here. So, you know, when yesterday and the day before, Pascal Vincent was telling you, you know, always try simple, and like something that's great with scikit-learn is that we did all that training. I guess a lot of you have reproduced it. It runs on your laptop like that, and you can do all those hyperparameter exploration, and you know, get a kind of a feel for your data set. And you know, maybe deep learning is going to work better, maybe not, but at least as a first pass, you should probably get on scikit-learn and try simple models. Because if it takes you 2 weeks to train a model, just to find that, you know, it overfits, that sucks. Yeah?
So, how are the correlations between features? Are they accounted for here? Does a linear regression like a multiple linear regression? Or is it like univariate linear regression?
So here, in a sense, if you were thinking about those plots, that's, you know, response function of time. You know, your predictors are time series. So really what you care about is the correlation between the betas, and here there's kind of, I mean, they're not going to be strong. And in any case, I mean, the way we validate our model here takes that into account. You know, it tells you if you can make good prediction, and in that you compound everything. Do I have a good parametric assumption, and can I estimate my beta well? And if there's some crazy correlation, the beta you should have in your fit, then that's going to decrease your generalization error. So here I believe like the regression model works with a simple, you know, independent, identically distributed assumption on the residuals, so it neglects potential correlation in the residuals. But, you know, in machine learning, essentially, as long as it doesn't impact our generalization error, it doesn't matter. So, you know, if you find a better training model that takes those into account, it performs better, good for you. Maybe you can try to publish that somewhere. Okay. Yeah, there was another question. Yeah?
How do you find novelty in the data?
Novelty?
Yes.
So there's a big trend we heard a lot during the main conference, which is to try essentially to fit a prediction model on sort of a steady state data. So I think Blake Richard showed beautiful data like that, where he was showing like random sort of ellipsoid to mice, poor mice, and they're almost blind too. It's really a painful thing to do to them. But anyway, he was showing them those random images, and then at some point he would show another image that followed a different distribution. And in a way, he had trained his model to detect, to be sensitive to those type of surprise. But what you could do here is simply try to predict the next image from the last one, and you would hope that it would work pretty well, and that when your prediction is very different from your actual input, then you have an index of surprise. So there was a poster by Peter Donhauser. He does his PhD with Sylvain Bayet, and he's preparing the paper on that, but he's used that exactly that approach to try to detect a surprise in text. So he did natural language processing, trying to predict the next phones or the next word in a text. He used like, I don't know, 80 hours of TED Talks to train his model, and then he can give a surprise index to any word, when the prediction of the model is very different from from what comes, then you get surprised. So that would be one way of trying to approach that. All right, we're almost, I don't want to delay lunch by too much, but I also want to talk a little bit about cross-validation. Unfortunately, I do not have a dedicated slide for this, for various reasons, but I can try at least to broadly discuss the main options that are offered to you. I would say the simplest you can do is called LOOC, leave one out cross-validation, LOOC. And when you do leave one out, what you do is that, say you have 100 examples. Your training set is going to be 99, and your test set is 1. But obviously, you don't want to just validate on one example. So what you're going to do is that you're going to loop through your data set, and the first time, the first example is a test, the second time, the second example is a test, the third time, the third example is a test. And that way, you're going to test every image once. All right. So what it means is that you've got 100 0 and 1s. 0 when you failed at your prediction, if we're talking about class prediction, and 1 when you were right. And you can average those, and you get an accuracy value based on all your 100 examples. So on paper, that sounds great, because you've got as much data as possible to train your model. And you didn't have lots of data, so you want to keep those good data to get a good model. And the evaluation maybe doesn't matter that much. So it's actually, in effect, it's a perfectly reasonable approach. It has also very simple statistics on it, because what you're doing is literally averaging 100 Bernoulli variables that have a certain probability to be 1. And so we can give confidence interval on those things. But there's a catch. You are messing up, even though it's very popular. And the catch is the way I understand it, and the motivation for not using leave one out cross-validation is that when I test the generalization of my model, I test more than that. I test also the generalization of me building the model. So when I do leave one out, all of my models have been trained essentially on the same data set, right? Every time it's my 100th time point, I've just suppressed 1. So yeah, the model is not going to be exactly the same, but come on. At least if you have a simple linear regression, your beta value is going to be essentially the same every time. So what I do in effect with the leave one out cross-validation is that I test the generalization of one model, which would use all the data. I do it cleanly, I do proper cross-validation, I don't use the test set data in my training data, but in practice there's so much overlap between my training data set that it's the same model I'm trying again and again. So if I say to people, look, it's excellent, I have 95% accuracy, I'm not lying, because I do have 95% accuracy on data I haven't seen, but if people use my algorithm on their data, they have a completely different model. I have no clue of the performance of their model. If I ship my model and they have data that's very comparable, then maybe that accuracy score is meaningful. But in general, in the literature, people are like, well, SVM is great for Alzheimer. I'm going to collect my own data. That's not what that score says. That score says that for the data of that person, with the model that person was using, that's how it worked. But we have no idea how it's going to generalize to a different research group with a different data set and a different model. Now let's take another sort of like completely opposite approach. We're going to say, you know what? I really want to understand how variable my model is. So I'm going to keep only half of my data points to train my model. And I'm going to repeat. Okay? So there's still going to be some overlap between my training set, but now that overlap is fairly minimal. If I take two subset of half of my sample randomly, the overlap is not that big. So I would guess quarter or something like that. I'm starting to be tired. I'm not going to try to do this little operation by hand, but it's small. Or at least smaller than 99%, like in leave one out cross-validation. And so now, essentially, I'm trying to test how variable my model is. And I'm going to test on the 50% that I left out. So I get now a much better idea of generalization. If I say, my accuracy 95%, that means that 95% of the time where I train my model, and on 95% of my example, on average, I was right. So now it's a much stronger claim, actually. Now, there's a catch when you do that, is because the test sets, the same individual is going to be seen many, many times, all right? Because every time you create a 50% test set, half of the people are in there. So if you repeat that like 1,000 times, you're going to see the same individual in many different test sets. So now it becomes actually pretty hard to put a confidence interval in your accuracy. So your accuracy has better interpretation. That's a point estimate in classical statistics. But it's actually becoming hard to make statistics on this. Which is why people typically don't do it. Now, all right. So those are kind of like extremes strategy. And if you want to be in the middle, you do 10% cross-validation. So you still have 90% of your data set for training, but you still explore a little bit the variability of your model. So when you have smaller data set, it's probably a pretty good trade-off. And now Gael Varocco has written a full paper to try to make his points that leave one out is a bad thing and you should use 10% cross-validation. So if you want to reference, there's one that just makes that very specific point. But in terms of the intuition for it, I think that's pretty much it.
What if we use a mixed approach with maybe 30% for the test set and leave one out for a validation test that would be used to set the hyperparameters? So,
70% or like 66% is very attractive to me.
Yeah.
It actually relates to bootstrap estimators and like subsampling estimators. And there was a burgeoning literature at some point where they were looking actually what proportion gives you the better estimate of the variability of your statistic. Because in a sense, that's what you're doing. You're bootstrapping or jackknifing or doing something like that to your model. And at some point, there was this idea of like Tucson would be a good thing. But it's old papers and they're not cited, not looked at. I don't know of a good reference that would really argue for what is the right proportion, but it's a complex problem because, as I said, it really depends on the underlying number of latent classes you have. If you have a data set where all the faces are the same, really your 10% test set is going to be a good representation of your data set every time. But if you've got lots of subclasses, you have vascular dementia, the mixed dementia, the Alzheimer's dementia, the Lewy body dementia, frontotemporal dementia, and you keep only 10%, you'll get Alzheimer 10%, vascular the other 10%, you get a very bad idea of your generalizability. So I don't think there can be a very good mathematical argument that would tell you, it's 2/3 or half or like it. Maybe you could, make an empirical evaluation of that, but it would need to be related to the actual question you're looking at and the type of data you're looking at.
So maybe it's more an open question, but do you think that nowadays deep learning is overfitting?
Yes, it is not an open question actually. It's clear that it does. So there's now some experiments where they try to take published model and there's a number of benchmarks that have been used again and again and again. And today you still have some papers which have theoretical contribution, or I shouldn't put quotes on, they have theoretical contributions, but then they're going to run MNIST and say, look, it works great. MNIST is that data set with digits that everybody uses. MNIST has been used so much at this stage, it's clearly community-based p-hacking, Same problem we have in imaging, and we've been discussing extensively in imaging for years now. But when you actually pull a new data set that hasn't been tried before, the performance all take a nosedive. Because you're looking at the best of the literature, which is essentially overfitting a particular benchmark. So for sure, when you have real test data, it's gonna come down. Now you have really good competition where they do have the held out data sets that they hide from the community and they don't organize competition that much, so it's hard to overfit that thing. But you really need to be very proactive, and I don't think that the machine learning community as a whole is first really understand that problem, because they're bad at stats generally, and second, as a best practice to advise them right now. I think actually the imaging community is doing very well in that respect, from what I've seen, compared to them.
You should mention maybe the Gale autism prediction challenge.
Oh yeah, yes, that's a beautiful example. So Gale hosted a competition to predict autism from functional MRI. And I think they had like pretty good result, 80% accuracy, balanced between controls and patients. So it's actually a pretty good score. Like saying everybody is a control would do 50% in that case. Yeah. So 80% is above, and significantly above. And interestingly, the winner had a better score on the hidden test set than on the validation set they gave them. And the reason that was given is that their test set was actually high quality. So the data they gave to the participants was of lower quality than the data they had as test set. And that's another issue with generalization. I mean, I very briefly mentioned about it, but when you generalize, typically you generalize to data comparable to yours. But then when you release it in the wild and it's applied in clinics, clinical trials, and things like that, different scanners, different mechs, different times of acquisition, different resolutions, all those things actually matter a lot. Especially if you've trained your data on a very narrow, single site, what they call clean, really doesn't represent variability at all. So, your clean data give you really shitty estimates of generalizability. And that's currently actually that even in imaging today, lots of people go by the claim that, you want a clean, pure data set with very controlled parameters. But from a machine learning perspective, it's a catastrophic stance. All right. Okay. So, one last, but I think we need to go our foot too. No, one last question. Go ahead.
Is there any kind of indicator for generalizability, and can we plot it like this and say when we have 50% of data sets for training, it is very generalizable, yeah. And then we go, and then do you think that would be computationally really hard to have, or is it going to be a flat line that is always going to be perfect when we have it like Luke compared to, or is there an optimum somewhere?
So, if you want to answer that question, you need lots of data sets that you pull and you see how well they generalize from each other. I know really like 2 papers that have done that. One by Gail Varosco's group and one by my group for fMRI. I'm talking about it's a very small niche thing. And I think the convergent result is that when you pull enough samples, then you start generalizing quite well to new sites that have very different characteristics. So that, as a rule of thumb, seems like a promising approach. And when it starts, people do, that generally they test something that's called the homoskedastic hypothesis, which is that the residual of your models, they all have the same distribution. And what they'll do is that if you compare 2 groups, they're going to compare the residual amplitude between those 2 groups. You can do that in machine learning. If you have 3 sites or 3 studies which you pulled, you can test if the accuracy is significantly different from one side to another. It's pretty easy to do. It's kind of like a quick test. Right. So thank you very much, and I'll see you after lunch.